Indonesia merupakan wilayah yang rentan terhadap bencana hidrometeorologis terkait kondisi atmosfer yang ekstrim seperti hujan lebat, banjir, longsor, puting beliung, dan kekeringan lahan. Oleh karena itu, Pusat Sains dan Teknologi Atmosfer atau PSTA merupakan pusat satuan kerja dari Lembaga Penerbangan dan Antariksa Nasional atau LAPAN yang bertugas melaksanakan kegiatan penelitian, pengembangan sains dan teknologi atmosfer serta pemanfaatannya untuk mendukung pembangunan nasional. Mengembangkan Satellite Disaster Early Warning System atau SADEWA merupakan sebuah sistem pendukung keputusan atau Decision Support System yang memberikan informasi peringatan dini bencana hidrometeorologis berbasis teknologi satelit dan model atmosfer. SADEWA berfungsi untuk memantau kondisi atmosfer secara real-time, memprediksi kemungkinan terjadinya bencana hidrometeorologis, dan memberikan informasi peringatan dini kepada pihak-pihak yang terkait dengan penanggulangan kejadian bencana seperti hujan ekstrim yang berpotensi menimbulkan bencana banjir dan longsor melalui website. Informasi prediksi yang diberikan oleh SADEWA diantaranya curah hujan resolusi 5 km, liputan awan, tekanan permukaan, uap air, suhu permukaan, dan prediksi angin. Pengembangan produk PSTA bertujuan untuk memandu kegiatan Litbang, memberikan dampak yang nyata bagi pembangunan nasional, meningkatkan akuntabilitas, serta mempererat kerjasama dengan mitra, pengguna, dan stakeholder lainnya. Indonesia memiliki potensi maritim yang melimpah, meliputi energi, mineral, minyak bumi, dan gas alam. Potensi produksi ikan tangkap yang sangat besar, perhubungan laut, dan pariwisata bahari dengan nilai ekonomi lebih dari 15.600 triliun rupiah per tahun. Oleh karena itu, pengamatan terhadap kondisi cuaca di laut sangat penting terkait keselamatan pelayaran bagi para nelayan yang menangkap ikan dan transportasi laut lainnya. Pusat Sains dan Teknologi Atmosfer (PSTA) merupakan pusat satuan kerja dari Lembaga Penerbangan dan Antariksa Nasional atau LAPAN yang bertugas melaksanakan kegiatan penelitian, pengembangan sains dan teknologi atmosfer serta pemanfaatannya untuk mendukung pembangunan nasional. Mengembangkan sistem embaran maritim atau SEMAR merupakan sebuah sistem pendukung keputusan atau Decision Support System yang bertujuan untuk meningkatkan produksi perikanan tangkap dan keselamatan pelayaran. SEMAR memberikan informasi kondisi atmosfer, informasi parameter air laut, zona potensi penangkapan ikan atau ZPPI untuk memudahkan proses penangkapan ikan, informasi posisi dan pergerakan kapal, serta komunikasi radio yang berfungsi untuk mendukung keselamatan pelayaran. Dengan menggunakan sistem pemantauan dan pengukuran berbasis satelit, radar, dan sensor di daratan maupun lautan secara real-time yang diinformasikan ke dalam website. Pengembangan produk PSTA bertujuan untuk memandu kegiatan Litbang, memberikan dampak yang nyata bagi pembangunan nasional, meningkatkan akuntabilitas, serta mempererat kerjasama dengan mitra, pengguna, dan stakeholder lainnya. Atmosfer adalah lapisan udara yang menyelimuti bumi. Komposisi atmosfer terdiri atas campuran berbagai gas seperti nitrogen, oksigen, argon, dan sejumlah kecil gas lain. Kualitas udara sangat bergantung pada komposisi kimia atmosfer yang menjadi standar kelayakan bagi kehidupan manusia dan makhluk hidup lainnya. Pusat Sains dan Teknologi Atmosfer (PSTA), Lembaga Penerbangan dan Antariksa Nasional (LAPAN) yang bertugas melaksanakan kegiatan penelitian dan pengembangan sains dan teknologi atmosfer serta pemanfaatannya untuk mendukung pembangunan nasional saat ini sedang mengembangkan DSS Sri Kandi, yaitu sistem pendukung keputusan yang bertujuan menyediakan informasi komposisi atmosfer Indonesia untuk mendukung pengambilan keputusan terkait kualitas udara sebagai dampak aktivitas manusia dan kebakaran hutan. Informasi utama Sri Kandi adalah parameter pencemar udara yang terdiri dari karbon monoksida, ozon, metan, sulfur dioksida, nitrogen dioksida, dan partikulat berbasis data satelit dan pengukuran in situ, serta prediksi dari model transport kimia 24 jam ke depan. Informasi ditampilkan secara online di website. Proses penerimaan dan pengolahan data in situ dan satelit, serta prediksi model di dalam DSS Sri Kandi, didukung dengan fasilitas komputer kinerja tinggi, serta laboratorium kimia PSTA untuk menyediakan informasi DSS Sri Kandi yang akurat. Pengembangan produk PSTA bertujuan untuk memandu kegiatan Litbang, memberikan dampak yang nyata bagi pembangunan nasional, meningkatkan akuntabilitas, serta mempererat kerjasama dengan mitra, pengguna, dan stakeholder lainnya.
Semakin hari semakin terasa panasnya, keringnya, tidak nyamannya. Perubahan iklim adalah tantangan global terbesar yang harus dihadapi generasi hari ini. Dampaknya yang nyata terasa dalam kehidupan sehari-hari hanya akan memburuk bila tidak ada aksi strategis untuk mengadaptasi keadaan ini. Sebagai negara rentan bencana alam, Indonesia diperkirakan akan menghadapi coastal flooding dan kekeringan berkepanjangan, juga badai tropis ekstrim yang mengancam jutaan jiwa. Bumi sesungguhnya telah mengalami perubahan iklim berulang kali dalam sejarahnya. Namun, pasca revolusi industri, kenaikan suhu menjadi lepas kendali karena lapisan atmosfer yang terselubung oleh gas karbon dioksida, metana, dan gas rumah kaca lainnya yang dihasilkan berbagai aktivitas manusia seperti kegiatan industri dan transportasi. Namun, mengatasinya bukan berarti mustahil. Wawasan akan perubahan iklim menjadi kunci yang esensial untuk bisa bertindak, beradaptasi, dan melakukan perencanaan strategis, terutama dalam skala nasional. Dengan mengetahui berbagai parameter yang bersangkutan dengan perubahan iklim, seperti temperatur permukaan, curah hujan, ketinggian permukaan laut, aksi akan energi terbarukan, tata guna lahan, juga kebijakan lainnya dapat direncanakan dengan bijak untuk mereduksi produksi gas rumah kaca. Dikembangkan oleh tim Pusat Sains dan Teknologi Atmosfer PSTA LAPAN, Sri Rama hadir sebagai sistem pendukung keputusan yang bertujuan untuk memberikan gambaran prediksi iklim di masa depan akibat terjadinya perubahan iklim. Sistem database Sri Rama memungkinkan untuk memunculkan data-data atmosferik dalam perspektif waktu yang luas, dalam paparan spasial, maupun grafik dua dimensi untuk mempermudah user membaca pola perubahan data yang diinginkan. Data ini adalah data-data atmosferik perubahan iklim global yang telah diolah dengan model iklim SeaChem yang kemudian di-scale down hingga ke skala nasional, lalu diolah hingga bisa mencapai resolusi spasial 14 km dengan skenario RCP 4.5. Sehingga, pemangku kebijakan dari skala kecamatan hingga skala nasional dapat merumuskan rencana aksinya berdasarkan area dan kapasitas potensinya masing-masing. Karena dampak perubahan iklim pada setiap daerah adalah unik, tergantung pada fenomena alam dan manusianya. Dengan selalu mengembangkan pengetahuan akan teknologi dan informasi terkini, Sri Rama telah membuka pandangan akan realita tentang fenomena perubahan iklim pada platform aplikasi web. Sehingga, Sri Rama tidak hanya menjadi sistem pendukung pengambil keputusan, namun juga menjadi gerbang informasi yang membuka kesempatan bagi berbagai pihak untuk bersama-sama beraksi mengadaptasi perubahan iklim untuk masa depan yang terjaga bagi generasi emas Indonesia.
Kondisi atmosfer yang dinamis di wilayah benua maritim Indonesia memberikan dampak yang luas terhadap pembangunan nasional di berbagai sektor seperti pertanian, kelautan dan perikanan, perhubungan, energi, kesehatan, lingkungan hidup, kebencanaan, dan sebagainya. Dengan demikian, informasi pengamatan kondisi atmosfer secara real-time serta prediksinya ke depan dengan jangkauan luas sangat penting untuk mendukung pengambilan keputusan kebijakan dan manajemen di berbagai sektor pembangunan. Hal ini perlu didukung oleh infrastruktur teknologi dan riset mengenai atmosfer. Untuk itu, Pusat Sains dan Teknologi Atmosfer atau PSTA yang merupakan bagian dari Deputi Bidang Sains Antariksa dan Atmosfer Lembaga Penerbangan dan Antariksa Nasional atau LAPAN mengembangkan sistem pendukung keputusan atau Decision Support System berbasis pengamatan, prediksi, dan pengetahuan sains atmosfer untuk mendukung pengambilan keputusan kebijakan dan manajemen oleh kementerian-kementerian terkait dalam rangka meningkatkan kinerja pembangunan. DSS merupakan sistem berbasis komputer yang interaktif dengan menggunakan sistem komputasi kinerja tinggi atau High Performance Computing atau HPC dengan memanfaatkan data dan informasi yang cepat, tepat, akurat, serta mudah diakses dan diperoleh. High Performance Computing menggunakan teknik komputasi paralel dengan memanfaatkan sejumlah komputer yang independen secara bersamaan dan dihubungkan dengan jaringan kecepatan tinggi dan mampu bekerja secara paralel untuk menyelesaikan suatu masalah. HPC dibutuhkan untuk menjalankan model atmosfer ekuator resolusi tinggi, terutama untuk simulasi, konveksi, dan curah hujan di wilayah benua maritim Indonesia yang luas dan kompleks. Untuk mendukung kegiatan penelitian, pengembangan, dan operasional DSS dinamika atmosfer ekuator, maka pada tahun 2017, Pusat Sains dan Teknologi Atmosfer membangun Atmospheric Science Data Center yang dirancang sebagai Data Center Tier 2 atau Redundant Components.
DSS ini didukung oleh infrastruktur High Performance Computing dan basis data yang terdiri dari banyak server yang bekerja secara simultan dan terus-menerus, serta real-time, sehingga perlu dipastikan bahwa seluruh sistem itu bekerja dengan baik dan tersedia secara terus-menerus, baik untuk memenuhi kebutuhan penelitian maupun pelayanan informasi. Untuk mendukung hal tersebut, dibutuhkan suatu kondisi lingkungan, ruangan server, yang stabil, terpantau, dan terkendali, termasuk pengendalian suhu dan kelembaban ruangan, pasokan listrik, keamanan dan keselamatan, pemeliharaan, dan stabilitas yang memenuhi persyaratan untuk mendukung sistem DSS.
Keberadaan data center sangat vital untuk mendukung kegiatan penelitian maupun pelayanan di lingkungan PSTA. Data center ini akan melindungi dan menjamin berjalannya sistem basis data dan sistem pengamatan, sistem simulasi atau prediksi berbasis High Performance Computing cluster yang ada di PSTA, serta server-server Decision Support System untuk melayani pengguna. Dengan adanya data center ini, diharapkan dapat meningkatkan kinerja dan produktivitas dari PSTA secara keseluruhan dalam rangka mendukung kegiatan pembangunan nasional.
Nature is beautiful. Not only about expansive ocean, but also the chain of islands, the span of mountains, and endless winding road. Nature is rich. But when talking about nature, it is also about the potential of natural disturbance. That comes any time, with no alarm. Natural disturbance is unpredictable. Technological advancement has taken us to a new chapter. Innovations were the foundation for every change, giving us hope, certainty, safety. A device that brings massive benefits. Extensive coverage monitoring system that send alerts and precise information to other devices that transmit signals to save our life from natural disasters. Remote Sensing Satellite by National Institute of Aeronautics and Space, LAPAN. Utilize and processing the satellite image data to map potential disaster, detect the fire spot, flood, and landslide. Hotspot detection results data produced by satellite image of LAPAN acquisition is utilized by the Agency for the Assessment and Application of Technology, BRIN-Kyoto, to apply AI-based weather modification technology to prevent forest fire. The artificial intelligence for forest and land fires is made using satellite image data and observation tools. And then the results are used in weather modification technology operations to reduce forest and land fires. LAPAN is developing A2 and A3 satellite, which generate automatic identification system, AIS data, to monitor ship movement. Besides LAPAN, BRIN-Kyoto is also developing AIS by utilizing transceiver-based radio frequency. AIS data is used for various needs, such as illegal fishing monitoring, ship accident prevention, and others. LAPAN is currently developing the LAPAN A4 and A5 satellite. LAPAN A4 satellite has built-in remote sensing to observe Earth's surface, mountains, and marine observations. A5 LAPAN satellite will have AIS, IoT, and other contents to connect various early warning sensors detector. Includes data communication with BRIN-Kyoto Tsunami Buoy. Module consists of different kinds of sensors, are planned to be used as an instrument of data communication between BRIN-Kyoto Indonesian Tsunami Early Warning System, TEWS, buoy in the sea, with ground stations on the land as a unity of an early warning system to reduce the impact of the tsunami. TEWS uses a DSS decision support system device, can process information obtained from a land and sea monitoring system to determine tsunami risk levels after earthquakes. As time goes by, natural disturbance become more uncontrollable. More and more disaster will occur in the future. However, we realize that innovation should never stop, because it is the key for having a peaceful life. Technological advancement has transformed an imaginary frontier into a real place to live. When spaces have no borders, all we need is acceleration that provoke thoughts to find an answer for every challenge. Today, connectivity is fundamental to accomplish developmental missions. Therefore, transportation that connects every corner is indispensable. Through scientific experiment, investigation, and advancement by an experienced technological institute, N219 and N219 Amphibia are made. N219. These are the future mode of transportation that, equipped with high readiness level, a paramount innovation. For fast mobility, to reach every remote destination with a runway of a solid land or soil under 1,000 meters, not only for a logistic and medical transport in disastrous area, N219 also make every beautiful destination reachable. Next development, N219 Amphibie. Air transportation that can take off and landing from land or sea. Equipped with landing gear to reach every beautiful corner of the country. Supporting tourism. Explore a new destination. N219 and N219 Amphibie, a mode of transportation for opening new frontiers to reach faraway places, undiscovered spaces. An innovation for exploring new horizon, the long-awaited answer for region-based connectivity. Technology has been a crucial component for developmental acceleration. Ensuring national security is not enough by deploying border guards. An integrated surveillance system is urgently needed, a system that can provide accurate information. From a long collaboration among research institutes in Indonesia, a future security device has been born. Elang Hitam, Medium Altitude Long Endurance UAV. An innovation and collaboration between Agency for the Assessment and Application of Technology, BPPT, and Indonesian Aircraft Industries, Dirgantara Indonesia. A medium-altitude long-endurance UAV with the same class as MQ-9 from USA and CH-4 from China. An innovation of defense system, the vanguard of Indonesian surveillance system. An intense and high-mobility drone. Its control system is integrated with the operating system. A device that monitors a vast area from the sky to safeguard the most remote corner in Indonesia. It strengthens our defense system, assuring the security in developing the country, ensuring the safety for every soul to grow.
Ladies and gentlemen, welcome back again in International Conference on Radio Science, Equatorial Atmospheric Science and Environment, INCRIS, and the 6th Asia Research Node ARN Symposium on Humanosphere Science. We will continue with the symposium and the scope of science including atmospheric science, environmental science, oceanography, space science, material science, plant science, entomology, microbiology, ecology, forestry, wood science, chemistry, biochemistry, molecular biology, architecture, electromagnetic engineering, agriculture, ocean science, and etc.
All right, Cecil, the symposium on the first session will be moderated by Dr. Irma Yuli Hastin. Dr. Irma is Senior Researcher in the Research Center of Atmospheric Science and Technology, BRIN. She successfully accomplished her bachelor degree, master degree, and a doctoral degree in the same university. It shows that how faithful she is in her university ITB. All right, moving forward to selected publication. To be honest, there are tons of her publications that we have to read in this session. But because of restricted time, we just read the latest publication of hers. All right, first publication, it has been accepted in 26 August 2021, entitled Convective Cold Pool Associated with Offshore Propagation of Convection System over the East Coast of Southern Sumatra, Indonesia, in Advances in Meteorology 2021. Okay, the second one, it's accepted in 16 September 2021 in Journal of Meteorological Society of Japan, entitled propagation of convective systems associated with early morning precipitation and different northerly background winds over Western Java. All right, moving forward to the selected awards of hers. We are honored to read that. First, she got research grant of PRN LPDP Respect BRIN 2020 to 2021. And also, I'm super amazed to read that, she got American Geophysical Union Travel Grant 2017, and the best of LAPAN Researcher 2016. And then please welcome Dr. Erma Yulhastin.
Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. We will move to the next session in this symposium. In this session, we have 3 keynote speakers. The first one, Professor Shigeo Yoden from Institute for Liberal Arts and Sciences, Kyoto University, Japan, will be delivered his presentation entitled Dynamical Influence of the Stratosphere of the Tropical Troposphere. Professor Yoden, the floor is yours.
Thank you very much, Elma-san. And let me start to sharing the desktop, I hope. So can you see my slide?
Yes. Yes, we do.
Okay, thank you very much. And it's very great honor for me to give this talk in this 20th anniversary of EAR. Let me start some congratulations on the 20th anniversary of the EAR. And this is a front page of the brochure for this time, Japan-Indonesia collaborative study on equatorial atmosphere. And I visited EAR 2003 only once, but took this, and you can see Yamamoto-san here and colleagues of LAPAN. And this occasion, we started KAGI 21. It's Kyoto University Active Geosphere Investigations for the 21st Century COE program of MEXT of Japan. And some of you may remember this emblem of KAGI 21 during that 5-year project. I was reading the project, and it's a combination of the graduate science, RASC, REACH, and also a DPRI of Kyoto University. And at that time, Tsuda-san provided me this nice summary of the activity of the atmospheric and oceanic part of KAGI 21. I'm sorry it's in Japanese, but I think you already seen this several times, and you understand from this diagram, from the surface up to the 500 kilometers to the ionosphere and the thermosphere. And here's the middle atmosphere, stratosphere, and the mesosphere. And at that time, Fukawa Sensei also led the big project, CPEA, coupling processes in the equatorial atmosphere for the 6-year project. It's a Kakenhi project of the mixed, and it's directly related to the EAR observations. EAR is the main body of this activity. And this photograph, you can see Sato-san, Hashiguchi-san, also Turi-san of the ITB. And I think the ER is the main body of these activities. At the same time, it's parallel with the Kagi 21, and Shiotani-san led one of the atmospheric component of this research subject, couple of variations among lower, middle, and upper atmospheres. And this is one of the example of the comparison of the ozone and water vapor measurement, direct measurement by Big Zonde. And I suppose this is a LAPAN campus or something. And the important thing is not only the research, but the educations. We have done the intensive international summer schools on the active geosphere. And this is a photograph of the first Kagi International Summer School 2004. And you may see Kato Sensei. I'm very sorry, we missed Kato Sensei last year in January. But we do remember his leadership and achievement in the tropical meteorology and also radio atmospheric science in these decades. And also would like to succeed to his spirits and dreams together. After that, there are several collaborative research and education programs. Okay, and here's one of the such kind of activities on the international workshop on prevention and mitigation of meteorological disasters in Southeast Asia. And this was taken as the Jayakarta Hotel in Bandung, I think. And here's the Tsuda Sensei. Okay. And also, a couple of years ago, we also done the JSPS Core program with the colleagues of ITB of Indonesia and Hanoi University of Science in Vietnam, and also Nanyang Technological University in Singapore. And we have done this kind of workshop of extreme weather in changing climate in the maritime continent. And also the schools, Southeast Asian school on the tropical atmospheric science. So these are continued international collaboration, both in research and educations. Now, let me summarize the uniqueness and the importance of tropical meteorology in this section. I hope you can see this animation. It's a GMS IR image for only 5 days. And you can see the contrast between the tropics and the extratropics. The difference comes from the source of the main energy. In the tropics, it's a moist convection, small scale, moist convection. On the other hand, mid-latitude is a volcanic instability with thousands of kilometers of scales. And in the tropics, moist processes consist of the water vapor, clouds, and precipitation, and couplings of the ground microphysics and radiative transfer process. And also the large-scale dynamics and thermodynamics is important. And we highlight this multi-scale dynamics associated with the moist convection and its organizations in wide ranges of space and time. So this is a summary of the spatial and temporal scales of atmospheric energy phenomena and processes. And this kind of multi-scale dynamics in the tropics is largely different from the counterpart in the extropicals. As I said, main energy input in the tropics is a cumulus convection, moist convection with this small spatial and temporal scales. On the other hand, energy input in mid-latitude is hundreds of thousands larger than space and time. And if we overlay the resolved ranges of the numerical models, global climate or numerical with that covers most of the extratropical cyclone scales. But cumulus convection is parameterized totally. Even in the regional numerical prediction models, still the limitation of the brief representation of the cumulus itself. This is the main issue. At the same time, this is a challenge in the tropical meteorology. The theoretical background is very different from the counterpart in the extratropics, mainly due to the small value of the Coriolis effect. And the dynamics is outside of the quasi-geostatistical framework in mid-latitude. At the same time, the observations and analysis are still limited. So even now, numerical weather predictions up to sub-seasonal to seasonal timescales remain in poor quality in the tropics. Also, climate projections for the 21st century have the largest uncertainty in the tropics. And also, I'd like to ask the role of the stratosphere. How was the role of this part just above the convective systems and their organizations? That's the main subject of this section, stratospheric influence on the tropical troposphere. And the WCRP SPARC project, we are doing the SATIO TCX research activities. It stands on the stratospheric and tropospheric influence on tropical convective systems. And Peter Haynes of Cambridge, Peter Hitchcock of Cornell, Sakazaki-san, Kyoto University, and myself taking the role of the activity leaders. And you can visit this URL to see the materials. And last year in February, we had a joint workshop, and just before the COVID-19, and there are several cancellations already, but I think 70 people met to this stratosphere, troposphere, dynamical coupling in the tropics. And very recently, we published 2 review papers, Hitchman et al. And also Haynes et al. And Haynes et al. Introduced this diagram. This shows 2 frameworks, QBO influence to the tropical troposphere, and sudden warming in the polar vortex, winter polar vortex, influence to the troposphere through 3 pathways: extratropical pathway, subtropical pathway, and tropical pathways. And the first one is the Horton-Tan relationship and vertical annular mode variations. Second pathway is related to the subtropical jet and its modulation. And the third pathway is the main target. And several processes include the dynamical, thermodynamical, processes. And these are very important key parameters to characterize the linkage. And also amplification mechanism also important. Okay. And here's a continuation of such kind of study. Yeah, we studied interrelationship between the QBO and the ENSO for their modulation of the QBO influence to the troposphere. And it's under the review. We have done the UF analysis, and this is the EF1 and EF2 for the lower part of the zonal mean zone in the equatorial region. And nearly 95% is explained only two first components. And this is PC1, PC2 phase space showing the rather similar amplitude, but the phase change with time. And this is only for the DJF Northern Hemisphere winter period. And we have made a composite difference analysis dividing the two opposite QBO phase groups. And I hope you can see these animations. This is a composite difference, G1 minus G2, for only La Nina phase for every 22.5 degrees. So in total, 60 angles along this. And you can see by the way, non-shaded area is significant statistically. And you can see the direct QBO signals here and disappears largely in the troposphere. And this is a Horton-Tan relationship. And here's a very significant response in polar regions and in some period down to the surface. And this is a mid-latitude response and also the tropical response. Similarly, we can see such kind of animations for all period. This is only El Nino. This is neutral. And this is La Nina period. By the way, this is very artificial. This is animation for each QBO phase, but fix the season. In the reality, there is a seasonal evolution, but we fixed and only see the dependence of the QBO angle, phase angles. And we can recognize previous studies and very clear Horton-Tan relation in La Nina period. And also in the temperature composite difference, we can see very clear signal in the tropical troposphere, opposite sign between the El Nino and the La Nina period. I think this is a new finding. Okay, and this is just a still image in any case of the travel of the animations. And here's a real image. No analysis data, but yeah, we reported another workshop report for EOS. And this is a snapshot of the Madden-Julian oscillation cloud, supercloud clusters. And this kind of size of organization of complex systems propagate slowly eastward. That's a Madden-Julian oscillation. But each component consists of this kind of aggregation of the convection systems. So multi-scale interaction from here to here. This is only the 10 kilometer depth and 10 kilometers width. But this is thousands of kilometers in horizontal. So that is the fundamental nature of this. And this meeting, the highlight was the QBO modulation of the Madden-Julian oscillations. And you and Son started this interesting work. And we just followed and made this kind of composite Hochmüller diagram for three QBO categories: easterly phase, westerly phase, or neutral phase of the QBO. And each of this is a composite of Euler anomaly, and this is a color scale, and this is a key date. along the equator from Greenwich to Daytona and Greenwich. And you can see in the easterly phase of QBO, stronger activity. Propagation speed is slower in the easterly phase, and also the longer lifetime. So this is consistent with the first report by Yu and Son. And recently, Martin et al. Made a very nice review work published in the Nature Review, Earth and the Environment. It's a new journal. And you can see whole the document PDF through this URL. And this is a QBO influence in the lower stratospheric and upper troposphere. Colder and higher tropopause in the easterly phase of QBO and opposite for the westerly. And that directly influences the MJO type of circulations. In the easterly phase of the QBO, increase MJO and strength and activity, and also the slower propagation and application. Predictability is increased for this phase. On the other hand, the westerly phase, faster propagation and low predictability. So using this diagram, we can summarize the QBO modulation of the, but let me start tropospheric part. In the tropical troposphere, there is a multi-scale interaction, the moisture convection. This is the main energy input with the longer time scales. And there is a periodic forcing of a diurnal cycle and seasonal cycle due to the rotation of the Earth and the revolution of the Earth around the sun. And we recognize the diurnal variation of the moisture convection, and also the monsoon is a periodic response to this time scale. And here's the interseasonal variation, tropical cyclones off the equator, and the MJO, Madden-Julian oscillation, along the equator. Internal time scales answer is a very important and clear signals in the several year time scale, and much longer climate change due to anthropogenic influence. And these variations have a large important societal impact through the flash flood, gusty wind, flood, economic activities, drought, and also the biodiversity in the much longer time scales. And we also include the influence, possible influence of strategic variations, including the sudden warming in the shorter time scale and international QBO, 11-year solar cycle, and also a longer time cooling trend in the stratosphere. And here's the example of the Madden-Julian oscillation. In the troposphere, there is a multi-scale interaction, but at the same time, there is a QBO modulations of this Madden-Julian oscillations. So this kind of a new framework to think about the variations. And we can apply for the monsoon systems. Monsoon is a periodic response of the tropical convective systems to the seasonal variation of the solar forcing. But at the same time, we can think about the QBO modulation of the monsoon. And this is underway in preparation, but this is a composite of the wind, precipitation, zonal means, and this is a horizontal distribution, precipitation, and wind. And this is June, July, August. This is DJ, and this is a difference of 2 seasons. So you can see the Northern Hemisphere monsoon systems, Asian monsoon, North American monsoon, and also the Southern Hemisphere. So Australia monsoon is directly to the maritime continent monsoons. And you can see the nice asymmetry and symmetry of this kind of zonal quantities. And this is a composite difference analysis of the particular phase of the QBO. And this slide shows the phase 4 minus phase 8. And you can see over the rectangle, these are very significant precipitation and opposite sign in OLR. And again, the same sign for the W, vertical wind in the middle troposphere. And this along the equator is characterized by the modulation of a Walker circulation. This is a climatology along the equator and UW wind and water vapor mixing ratio and the largest precipitation. I think this is only the 90 degrees to 235. And here's a Papua New Guinea, and this is the Kalimantan. Okay, so largest precipitation. And this is a QBO modulation of this. And I think this longitude significant. And that difference, significant difference comes from the phase 8, suppression of the precipitation over these regions and consistent with the larger value of the OLR and surface pressures. So let me summarize, conclude my presentations. I showed the diametrical influence of the stratosphere on the tropical troposphere and mostly under the WCR Spark 30 TCS activities. And please visit our web page here. And there you can find the new review papers published in the Journal of Meteorological Society Japan this year. And also this link, you can see the PDF file of a Martin et al. Review paper. It's a very hot subject, very focused QBO modulation of the MJO, but already in over 100 papers in the past 5 years. And also I added some new findings based on the composite difference analysis like this. And I several times use this kind of possible stratus influence to the multi-scale interactions in the troposphere associated with the moist convection and its organization with this kind of time scales. So currently, along this line, we are doing another project of the extreme weather in changing climate in the maritime continent. And the important keyword is societal applications. By the way, this symposium is a joint symposium increase and 6th Asia Research Node Symposium on Human Sphere Science. This part increase is a scientific basis for this extreme weather phenomena in changing climate. And it's important, not only in the tropics, but it's remote and global influences, teleconnections, and also these quantities, wind, temperature, precipitation, and such kind of thing. But another symposium main target is a relationship with the society. So we can ask the impact of this kind of extreme weather phenomena on society and preparedness, mitigation, and adaptation to this kind of extreme weather. So this covers social science, humanity, engineering, agriculture, medical science, etc. And human sphere science requires intimate collaborations among these kind of multi-interdisciplinary disciplines. Okay. So I think, I would stop here. And in the last decade or more, we presented this kind of dream for the establishment of a new Southeast Asian Center for Research and Focus on Weather, Environment, and Climate, both basic science and also for the applications. Okay. Thank you very much for your attention. Terima kasih.
Thank you very much, Professor Yoden. Thank you for your great presentation about stratospheric dynamic role on troposphere related to global phenomena, such as MGO and ENSO. It is very essential to deal with under the global warming issues in particular. So next, I will invite Professor Zhang Kyung Liu from National Central University, Taiwan. Professor Liu will be presented his work entitled Equatorial Ionosphere Weather Observed by Formosat 3 or Cosmic and Formosat 7 or Cosmic 2. Professor Liu, please, time is yours.
Okay, thank you. Yeah, first of all, I would like to congratulate the 20 years anniversary for the Equatorial Atmosphere Radar. And I also would like to thank meeting organizer invite me to give a talk over here because this is really mean a lot because I was staying most of my time in my early career in Kyoto University. So Kyoto University actually is, I should most collaborate, the university in my life. Meanwhile, I also like to give the credit and back to, during the, late 90s. So I have been working with LAPAN. And actually I I set up the Anasong over the Pali, and also have a lot of activity with the BMKG. Together, I've been, equatorial EAR radar site twice. And in fact, I should also go back to, I was stay over the Mu radar site for months during my sabbatical year. And my talk actually going to focus on the equatorial ionosphere weather observed by Formosat 3 and Formosat 7. And, I'm going to cover the introduction. So I'll give a brief about Formosat 3 and Formosat 7. Also like to mention some so-called prominent feature over the equatorial ionosphere. That include the EIA, equatorial ionization anomaly, wave number 4 being well known, the coupling between the troposphere and ionosphere, and also plasma depression bay and some new feature. Together, because we have several scientists that mentioned tsunami, and I'm going to talk about a little bit about the earthquake, ionosphere tsunami, and earthquake and tsunami disturbances. Finally, we actually it took us more than a dozen years. We finally will be able to, the so-called monitor the ionosphere, and also nowcast the ionosphere weather, and also forecast the ionosphere, weather. Together, I will cover a little bit about the S4 simulation and the monitoring and forecast that's related to the, the communication and positioning and etc. Come to the conclusion and finally come to conclusion. The Formosat 3 it was launched in 2006 and April, and by then it was only for 5 years. And it happened, as you can tell, it's more than 15 years. So it's a very long life. And the focus point is going to study the atmosphere and the weather forecast. Actually, that was the main mission. And the ionosphere actually is monitoring. The major technique I'm going to show over here is a GPS radio occultation. That's you transmit GPS. We just received the GPS signal by a LEO satellite. So cut through the ionosphere and the troposphere and the stratosphere. So therefore, we will be able to observe the water vapor pressure and the temperature up to 40 or 60 kilometer altitude, actually from about the sea surface up to very high. And the other, meanwhile, it will be observed the electron density from 90 up to 800 kilometer for the electron density. In fact, this is one of most suitable, one of the best, the instrument will be able to study the so-called atmosphere and ionosphere coupling. So as we see many times being mentioned for the SSW, for the ENSO, and the ENSO warm, ENSO cold, and all the, including later on, I will show you the ITCZ. So all the signature. Up to now, there's collected more than 7 million profile, to be able to understand the three-dimensionally, uniformly, the signature. So on right top, actually, is the green dot stand for the Formosa SS3 radio occultation observation. Blue dot blue triangle stand for the GPS location. So and the red star stand for the largest satellite, the observation like Mu radar and also the equatorial radar and those sites. And so coverage of the Formosa SS3 cosmic and actually RO is much more uniform and much more dense. And similarly for the atmospheric sounding, and the red spots stand for the radio sound. The green dot stand for the atmosphere, the Formosa SS3 cosmic, the atmospheric sounding. So following the success of actually the Formosa SS3 cosmic was decommissioned in 2020, last May actually. And following that, they have a successor, is the Formosa SS7 cosmic 2. This is stuff from 2019 June, and now currently observed. And again, still collect the electron density and together with this water vapor pressure together with the temperature. So actually, there's a name for that. This is the most accurate atmospheric thermometer of the world, and also the most uniform, the ionosphere sounding of the world. So this is for 6 satellite against the 6 satellite. This is American against US and Taiwan collaboration with the NOAA and NSPO. And the bottom, this is a satellite track on the left bottom, and for the right button stand for the observation. In fact, it's very fast. Actually, it's almost one day it collect, more than 5,000, the atmosphere and the ionosphere profile. So this provides us a very uniform, but this one, because it's a low inclination for 24, so it's only cover up to 35 and 50, around 45, the latitude for the both hemisphere. And this is the main payload is so-called Tri-G. That means Tri-GNSS radio occultation system. So therefore, due to the Tri-G, it's not only the GPS. So it's allow us to collect many occultation and many, the atmosphere and ionosphere profile. And certainly they also have other payload like ionosphere, the ion velocity meter and something else. And I prefer, actually the main mission of the Formosa SS3 is weather forecast and the climate. So I will show you a little bit about this one. And this is the observation of the one of severe the typhoon, with a very strong precipitation. And actually with the Formosa SS3, and it's actually that you can see that during Typhoon Monaco, it's very serious. So this is not on the river, actually it's in the downtown. So you can tell that in 3 days, it's actually collected almost 2 meters high water. So it's very serious. This is a harbor. When the harbor was blocked by those tree trunk, it was to take 3 days to empty that. So the severe weather actually was the main purpose to be able to provide, the service of Formosa SS 3 and 7. If we have a Formosa SS7, you can tell that the brown one stands for the model prediction. The purple and the yellow one is observation and Formosa SS, the 3 and the Formosa SS7. If we have that one, we will be able to collect that one, very accurately. So this is a powerful tool not only for the, it's a major is for the weather, but we, ionosphere scientists take the advantage to study the ionosphere space weather. And the advantage of the radio occultation that allow us to look at the ionosphere with three-dimensionally and globally. And so that will be able to see like a 3-dimension. As you can tell, there's a several cut from -120, -60, -0, -60, and 120, and 180. Is one example. So the latitude and altitude and latitude cut. And this is the horizontal slice. That's a 300 kilometer, 250, and 200 and 100. So this electron density will be able to see the old ionosphere weather and how that evolved. This is a movie, and you can see the older detail. And due to the 3-dimensional study, we see some so-called plasma cave or plasma tunnel. You can see that over here. This was actually right under the EIA crust. EIA crust was observed during the 1939, something like that. And after 60 years, more than 60 years, we finally, by using the Formosa 3 cosmic, we see that this is very funny signature. And you might wonder what will be the effect on our ionosphere communication. Like for the FHF communication, the wave could be trapped and also could be delayed. So the larger, so whenever we have applied like a fishing boat, you communicate with this one, it's going to have a serious problem. So actually I would like, the one of the reasons I would like to demonstrate is that the Formosa 3 actually has been a long-term observation over the, EAR, the site. And this is the site that we collected during the period. I want to demonstrate that and how that affected. And this over the region. So this will provide a very good one. So if anybody would to study the, the so-called AI coupling with over ER, the database, this will be also provide a very good one. So this is the so-called the F2 peak and the electron density, and together with this, the HMF2. Over the ER in the various months. This is during March, this during the September, this during the June. So one thing I also noticed, actually this plot just produced, that few days ago. We observed a very interesting for HMF2. Actually over the ER site, during the March and during the December, for some reason, they have a 2 double peak, but for the other one, they don't. So this is something maybe worth to compare with this, the ER site, to see how that the mechanism. So this is some kind of new finding. Hopefully we will have chances to be enhanced such a study. Regarding the low and equatorial latitude ionosphere, and so-called we're going to show you the equatorial ionization anomaly and the plasma cave which I already show, and also with this, the wave number 4 and the plasma depression bay. This is the cut from the 01, 03, 05, 05, 30. So you can tell this is during the August and July, and this is a North Hemisphere. This is a cut over the 120 along the Taiwan longitude. So the white line stands for the magnetic field line. So the wind blow this one from ionization sunshine over here from around 6:30, then start to push by the the transequatorial wind and pile up over there, the South Hemisphere. I just let you know. Here is around Indonesia. Okay, Taiwan actually is conjugated with Pali or like the places. So actually it's cut through the both between Taiwan and the Indonesia. So in this case, actually you can see the old evolve, and finally the winds start to stop about the 130, then start to pile up over the the summer hemisphere. So I just, as I mentioned, for solar radiation effect, asymmetry neutral wind composition, and the summer to winter, transequatorial wind, and the plasma, fountain effect, and plasma cave fish signature. So this is actually the very powerful tool where we'll see something. And I would also like to mention for the troposphere and ionosphere coupling, It's famous so-called ICTZ convection zone. And the bottom side is the so-called the ICTZ zone, as you can everybody understand. This is looked at from our water vapor and those stuff and the humidity. So we compare that, and you can see the 1-to-1. This actually is a so-called the DE3, the non-migrating tide. There will be a tidal signature coupling between the lower part and the ionosphere. I just draw your attention. Actually, the Kododaban is around here. So it's very useful for the future study. We can study in some more detail by using the Formosa 3, the data. And similarly for Formosa 3, and you can see that in various months, the EIA actually you can see that in various the location, and that's for the so-called for the October, November, December. This is a daytime phenomena. For the nighttime, and you can see the depression bay. So all the 1, 2, 3, 1, 2, 3. So I can draw your attention. The Kododaban is over the one of a bay, and also under one of the EIA number green tide. So this is also again, if we can somehow with a more comprehensive, the EIA, the equatorial atmosphere radar, EAR, the data support, so we will be able to uncover the much more detail with not only the low atmosphere, but also the higher altitude. And we look at that one by using model, we can see the wind blow that over, cast, the such kind of a compression and the result in the depression bay. And so similarly, actually, it's not only the Formosa 3, the recent, the so-called Formosa 7, you can see the very similar signature, and which is those are base structure for number 4, and the best part of the wave number 4 and the depression base signature by using the Formosa 3 because they have the IVM. So not only the electron density, which is a radial occultation from 500, 400, 300, and this is 200. And also you will see the velocity, the ion drift, which is a northward, the upward, and the temperature, and in the ion temperature, ion density. So this provides much more so-called understanding on the the mechanism, physical mechanism. We understand how the plasma was influenced by the tidal from the troposphere, was affected by the neutron, and how that the plasma responds. And so once again, Formosa 3 and Formosa 7 provide the 3-dimensional structure and dynamics, and especially for the the low latitude and the equatorial ionosphere with the wave number 4 and the plasma depression bay. And depression bay actually wave number 4 actually was significantly affected by the E cross B outward drift. This comes from the convection ITCZ. So we can uncover that one with the Kododaban's radar more information. And the PDB actually is, like I say, is many come from summer to winter neutral wind. And IVM will uncover the physical mechanism of the plasma physics. The transfer signature, because we talk about tsunami, and if a tsunami come in, they will perturb the atmospheric perturbation and affect the ionosphere, the perturbation, and together with the signature. In fact, the first of the ionosphere signature by using the GPS was observed over the Sumatra, and this is the one before the the tsunami arrived, and you can see it oscillate with that one, and for the similarly for the Japan, this is the GPS station, and this is the monitoring by using the GPS and ionosphere. So you can see from the even ocean surface pop up, and we can go to the ionosphere. And this is give us the chances to be able to monitor the tsunami early warning. And whatever, if you have a ground-based, the GPS receiver, but not only ground-based, I will show you from the space. And so this is the one of during the Togo, the earthquake, and this is the oscillation right up, after the earthquake occurred. And this is those spots for the radial occultation. The red one stands for the signature being detected. Blue one also stands for the signature being detected, but not so strong. And we will show you. And this is the ground base of the GPS observed. And this is the top panel. You can see that this is the perturbation by the tsunami, and this is perturbation by the radio wave. And you can see this altitude, this is the time with each profile, and the location you already see. And you can see that once they go, all the ionosphere can be perturbed. So Formosa 7 actually will be able to help us to understand to confirm the signature over there. In fact, this kind of a technique has been used for even the latest Sulawesi in the 2018, the signature, we actually successfully detect that one, the signature. And I'm not going to talk about too much detail. And you can see the perturbation actually enhanced its energy, much more stronger after the tsunami and the earthquake perturb. So Formosa 3 and Formosa 7 actually can be powerful tool to be able to see the lithosphere triggering by the earthquake, tsunami. Actually, I didn't show the volcano eruption and typhoon and magnetic storm. And everything we can see from this very powerful tool by using existing GPS satellite. And I will talk about the 3 model. And the 3 model actually is very similar to the current weather model. In fact, because we have Formosa 3, uniform observation of the ionosphere. For the first time, we will be able to develop so-called ionosphere monitoring, the very global so-called GIM map, so-called TGIM. And the other one, we will now cast that and we'll show you the power of that and also show you an ionosphere forecaster. So now we can see the ionosphere weather forecast similar to the weather. In fact, this is already been routine of prediction and the forecast published by the CWB in Taiwan, Central Weather Bureau. And finally, I'm going to also show you the ionosphere scintillation model. This is what going to help to understand and predict your so-called the interference or the communication quality over the any place you want to be observed. And I will show you over the Korodaba, okay, later on. I'm sorry, this is the older data. It's just produced. It's actually a few hours ago even. This is the GIM. This is the GPS. Usually we build a GIM. We use it only on a red dot. Over the ocean area, no data. So if we inject Formosa 3 or Formosa 7 data over there by using a common filter, and we can show you what we got. The top panel is a so-called TGIM, Taiwan GIM. And you can see that we have a very 10 minutes, it's a high resolution. And with all the data cover ocean area even. And this is a routine, the GIM published by the one of center, so code. That's the one in Switzerland. So as you can tell, with much more accuracy, much more high resolution, with the Formosa 3 support, Formosa 7 and Formosa 3 support. And now we're going to nowcast model. Nowcast model, we use this II model and inject the data into the measurement to fill up and change the data and shift that one to forecast 1 hour. And we're routinely running like this way. I showed you that this semi-3 was truth. This is a background model, it's a guess. And this is the, by using without, forecast, but this is with forecast. I just draw your attention to truth and with forecast, they match beautifully. And, on the contrary, if you look at II, they got poorly presented with this such kind of arrangement. Also, without the forecast technique, we won't be able to, correctly to predict the model. This is the OC. I will show you with once again, this also will be able to, with the Formosa 7, and we can also predict that. Unfortunately, Formosa 7 doesn't cover high latitude. So the high latitude of, reproduce, this is currently with this one. It's a little bit worse than if we have a higher altitudes, high latitudes observation satellite. This is the current model published by the also CWB. And this is every hour, you can see that. And on the left, that's a UT time frame. This is on the LT time frame. And you can see all the detail if you like to see the data. And it is dot stand for the sounding. So that's meaning we have a lot of data cover that all the stuff all together. And this is again some other so-called weather forecast model, this data simulation. This is a TIGC model plus with the Formosa 3 or 7. with electron density profile plus a dot. So this dot is actually was being used by the Wolf model. I think for the adversary group, they know that well. So we actually did the same thing. Currently, if we inject that one, this control and truth and compare with error, and we can find that with the Formosa SS3, we reduce error by 4%. If we Formosa 7, we reduce 8%. That's meaning much more improved. And this is the one of a site. You can look at the site and give you 6 hours predict ionosphere forecast over Taiwan. And actually for the global, okay? So if you like to see that what the ionosphere weather over your place, you can do that. So there's a 3 models that we developed for the communication and also in a positioning calibration. We have a very powerful monitoring, nowcast and focus model because we have a Formosa SS7. Scintillation been known, and this is on the this panel was published. This panel was published by the BASU, and this is the worst case of the scintillation. This is from noon to midnight, and as you can tell, they have a double peak. But for the solar minima, they don't have, and also ended by the midnight. For Formosa SS3, we finally. But by the way, this one was constructed by local virtual radar and the ground and some geostationary satellite. But with this Formosa SS3, and you can see all the detail with high solar, you have double peak, low solar also double peak, and actually start from the dusk to dawn. So actually it's over the midnight, so give much more information. So this is a radio occultation with those study, and this is with a global so-called distribution map, and you can see that during the September. We will be able to see the detail, somehow skip automatically. And with the Formosa 7, this is over the we can see the different altitude scintillation. Together, we also see the different level. This on the ground. I can see where is the most the dangerous place. This is over the Kototapan, and this is from the 2007, and this is all the each month. You can see that this altitude, this intensity, and this solar activity. You can see that over the Kototapan, the irregularity actually go up very high during the relatively high, solar activity. And we have a more, the Formosa SS7. What we can see, this is for Formosa SS3 for the whatever you see just for the month. But if we look at the 1 hour, this is only they can shoot it. Remark, okay, scintillation actually come from the F region and also E region. And GNSS Formosa SS3 and 7 can help us to have a better understanding on the position and navigation and communication. Like I say, I already showed that, we will see the equatorial radar, equatorial ionosphere over the Kototapan or anywhere you would like to, so this is the best chance we would like to provide our data set, and we'll be able together with this ER radar site, be able to understand all the detail over the equatorial area. So I'll come to my conclusion. Formosa SS3 cosmic radio occultation is a powerful tool for the ionosphere and atmospheric climate study. And Formosa 7 is this ongoing project. Ionosphere, the radio occultation is globally observed the 3-dimension electron density and dynamics, and in the equatorial ionosphere and the atmosphere. Formosa SS7 cosmic makes the ionosphere monitoring and nowcast forecast scintillation model being possible. This is for the first time. Okay, so 60 years after the weather forecast, which is a significant impact the research of the ionosphere scientists, as well as application of the positioning, navigation, and communication. And the Formosa said, the TGIS, because it uses GLONASS, GPS, and Galileo. And together with this IVM, that's a better understanding of ionosphere plasma physics, especially for the low latitude and equatorial ionosphere. And, Formosa 7 Cosmic 2 shall open a new chapter for the ionosphere weather and tsunami early warning. So we wish this could help everybody over the future, especially. I forgot to mention that We actually have a very good database for the middle latitude, also high latitude. Currently, Formosa 7 Casimir 2 also cover up to the Japan. So we wish will be in the future. We have a very intense collaboration with this EAR and the Mu Radar, the scientific group. Okay, and together certainly with this Indonesian and Japanese scientists. This concludes my talk. Thank you very much. Terima kasih.
I will talk about ionospheric weather variability over equatorial region, capturing by Formosat or cosmic data, and also possibility applied for detecting tsunami. So, ladies and gentlemen, the last keynote speaker is Dr. Didi Satyadi, Head of Research Center of Atmospheric Science and Technology, National Agency of Research and Innovation, BRIN, will be talk about the past and future use of the equatorial atmospheric radar in atmospheric research in Indonesia. Dr. Didi Satyadi, please come forward.
Yes, thank you, Irma, for the opportunity. Good afternoon, everyone. Allow me to introduce myself. My name is Didi Satyadi from the Research Center for Atmospheric Science and Technology, LAPAN. A problem with the screen sharing. Let me try again. Yes, can you see my slide?
Yes, yes.
Yes, which is now part of the National Research and Innovation Agency. I'm actually, I was a student of Professor Yoden during KAGIT 21 at ITB. Sorry. Apologize, everyone. I think I have problem with my slide. Yes, to continue, this is the outline of my presentation. First, the introduction, and next I would describe briefly about the ER and the past use of ER and some significant result. And in particular, I would like to share with you our study of atmospheric convections at our center, and also further study on the coupling process and the future use of ER or MU radar and the summary. So, ladies and gentlemen, as already mentioned by Professor Yoden earlier, the equatorial continent maritime is quite a special region with a large amount of solar radiation, which of course drive atmospheric convections, producing large amount of precipitation that drives local and also global circulation. And the atmospheric dynamics in this region, of course, is governed mainly by hydrostatic forces, which are gravity and buoyancy. And if they are in balance, they create waves. And if they are in balance, creating convection, which are interacting with each other. And as we know, the accurate information on weather and climate is important in this continent maritime agrarian region, and also a region prone to hydrometeorological disasters. But of course, it is a challenge due to complex and turbulent nature of the atmospheric dynamics in this region. So the advancement of knowledge of atmospheric dynamics in this region is the key to improve our understanding and to improve prediction performance in this region. And the ER has improved our understanding of atmospheric dynamics in this region and has the potential to improve prediction in this region. So this cartoon actually illustrates the complexity of the dynamics in the region. For example, it is a region of high energy and the key source of uncertainty to climate change. And it is an extreme region which is difficult to predict and require high resolution observation and also modeling. And it is governed by gravity and buoyancy and dominated by the coupling between convection and wave and multi-scale interactions, complex topography, and also land, ocean, and atmosphere interactions. It is the most complex region, but at the moment, lack of observation, understanding, and also model representation. And this is the equatorial atmosphere radar, which is developed since 1980s and operated since 2001 through collaboration, long-standing collaboration between Kyoto University and LAPAN, with the objective to advance the dynamical and electrodynamical coupling processes in the equatorial atmosphere from the near surface to the upper atmosphere. And this slide shows other supporting instrument at the ER site, which is useful to observe the troposphere and also the upper atmosphere. And I think the ER and other supporting instruments have produced new findings, important knowledge, and improve our understanding in atmospheric dynamics in the equatorial region. For example, on the atmospheric convections and its interaction with the MGO, monsoon, etc., the atmospheric gravity wave generation by deep convections, also dynamical coupling between equatorial atmosphere and ionosphere. The tropopause layer, instabilities and also breaking, the troposphere-stratosphere exchange and transport of atmospheric constituents, equatorial plasma bubbles and ionospheric irregularities, and ionosphere, mesosphere, thermosphere interactions, and also in atmospheric modeling. And this understanding are important to fill the gap in atmospheric science, as well as their application in modeling and prediction of weather and climates. Now I would like to move on to our investigation of the study of atmospheric convections utilizing the equatorial atmosphere radar. So research was conducted at LAPAN to investigate convection trigger based on ER and other instruments at Kota Tabang, because the problem of convective trigger is important and at the moment still outstanding problem in atmospheric science. In this study, we used the ER, the boundary layer radar, the sound detection and ranging, or SODAR, the radiometer, optical range gauge, and radio sound campaigns with the corresponding vertical range, resolution, and time. So this figure shows observation of an individual convective activities. This showing diurnal time and height cross sections of the vertical wind component observed by ER, showing this development of updraft and downdraft, and which is also shown here by high turbulence and echo power observed by ER, and increase in air density as observed by radiometer. And we can see also here downdraft due to rain observed by the boundary layer radar. And this correlates well with the occurrence of rainfall observed by the optical rain gauge. And this figure is showing the same event, convection event observed from the X-band radar, showing this maximum cloud cover at 17 p.m. and also showing here from the GMS satellite, showing that the convection event at Kota Tabang is part of score line development along the Sumatra island. And here we try to analyze using diurnal statistic or probability in the long term between 2001 and 2006. And we can see here in this figure time and height cross sections of updraft component from the ER, showing high probability of updraft in the afternoon over the Kota Tabang. And this showing the spectral width, turbulence, and also echo power, and air density from the radiometer. And here we can see the vertical wind component. Interestingly, it is showing indication of melting layer at around 5 kilometers. And here, the updraft is corresponding with the convective rainfall probability which occur in the afternoon. And here we see another figure showing updraft from the boundary layer radar and downdraft, and also the updraft from the sound and detection and ranging, which occur early from around 9 a.m. in the morning. And this showing turbulence and echo power from the boundary layer radar. And this from radio sonde campaigns, we plot the atmospheric instability showing the increase of the destabilization in the afternoon. And here we were trying to analyze seasonal statistic or probability using ER here, and showing the opposite direction of wind in the lower and upper troposphere, and also the reversal of meridional wind in around April and November in Kota Tabang. And here we can see the downdraft from the boundary layer radar in April and November, and increase of air density and maximum rainfall, which correlates well with the above observation at around April in November. And this figure on the bottom right actually illustrating the observation here, which is governed mainly by the sun gleam. And ladies and gentlemen, here we try to correlate between the destabilization of the atmosphere here, and then the initial updraft observed from SODAR from the surface until around 600 or 700 meters, and the corresponding downdraft from a boundary layer radar, and also from the equatorial atmosphere radar, which are correlating very well. And here we try to analyze the diurnal statistics from radiation campaign, showing the statistic of increasing instability, as shown here, indicated by the value of K, which correspond to the increase of cloud base or level of lifting condensation level, and the decrease of level of free convections here, and the decrease of inhibition. And we think that the decrease of inhibition is caused by the merging of increasing cloud base and decreasing level of free convection, which cause this difference becomes very small, which cause the inhibition is very small. And these large-scale instabilities combined with small inhibition trigger the convection at the Kota Tabang. And in this figure, we try to analyze rainfall and also CAPE data from radiation campaigns at Kota Tabang station, which show the indication of self-organized criticality behavior. And this figure at the bottom illustrates the self-organized criticality behavior by the sun fire experiment, where the sun will be accumulating here, and at one point it will achieve criticality and create an avalanche. And as we can see here, this is the data of rainfall size. And if you plot the log graph between event size and frequency, it produces a straight line, which is an indication of self-organized criticality. And this also shown by the radiation instabilities data, which indicate the self-organized criticality behavior. And the meaning of this is that instabilities were accumulated up to a critical point before converted into convective motion. And here we try to compare between the model and observation. And the left figures here come from the model, and the right figures come from the observation, showing a good agreement, except that the temperature of the tropopause seems to be lower here than in the model. And so we try to think about the trigger development at Kota Tabang. And here we think about the scenario of large-scale destabilization, increases instabilities, which push the LFC down, whereas here the boundary layer uprising push the level, lifting condensation level up, and this showing the evolution of the LFC, LCL, and LNB. And from this, we propose a new trigger based on large-scale destabilization rate and also local cell inhibitions. And the criteria is that the change of K from large scale must be large enough, and the inhibition energy must be small enough for convection to occur. And we try this experiment in the model, and at the bottom here showing somewhat better rainfall spatial feature compared to the original model, compared to the TRMM observation. And these investigations currently still ongoing to find the best trigger, convective trigger development for this region. And next, I would like to briefly describe the other result on the coupling process in the equatorial atmosphere. And this is the highlight from CPAA taken from presentation by the late Professor Fukau. The CPA has revealed new aspect of the coupling process and a unique feature of convection during different MJO phase, and also the breaking of Kelvin wave at the tropopause and excitation of gravity wave, and also coupling between E and F region and plasma bubbles, as you can see here from this figure showing the breaking of the Kelvin wave directly observed from the equatorial data, where the X here show the cold point tropopause showing the breaking and also the increase of turbulence, which may play important role in air mass exchange between stratosphere and the troposphere. And here, taken from Dhaka et al. 2005, showing the transport of momentum flux from the troposphere to the stratosphere. And here, taken from Hokke and Suda 2001, the correlation between this topography and convection in the troposphere and lower stratospheric gravity waves and sporadic E layer variability. All right, ladies and gentlemen, now I would like to move on to potential future use of ER and MU radar. I think this is important to study the coupling process in the solar terrestrial system, and also continue the study of atmospheric convections, and also multi-scale interaction between large scale to the local scale, and study of atmospheric wave and its relationship to global atmospheric circulation, and important for model development, the whole atmosphere model development, and also validation such as whole atmosphere community climate model and Gaia, and important in the study of radio propagation in the ionosphere, the ozone layer, the photochemical gases transport, the ice cloud in the mesosphere, stratospheric warming, atmospheric tide, and also climate change. And this is the planned development of the MU radar, as already explained in the morning by Professor Yamamoto. It is will be developed at the same site as the ER, which is a larger radar than the previous, which is 160 meter diameter with a larger output power, 500 kilowatt, and 10 times more sensitive than the ER. And this use of MU radar will be open to international research community. And I would like to inform you here that the planned development of MU radar is actually in line with the Indonesia Space Master Plan, which is the Presidential Regulation number 45, year 2017. And here I would like to show you illustration of integrated atmosphere space observation to support decision support system. Of course, this observation of the atmosphere from the troposphere, stratosphere up to thermosphere and exosphere are important to produce observation data and new finding and knowledge and scientific publication. But it's also important for validation, assimilation, and development of whole atmosphere model, which can support the decision support system here to the observation and also the modeling. And this will be important, will have important application and benefit for many areas as like prediction of space weather, radio navigation, radio communication, transportation safety, disaster management, prediction of terrestrial weather, and also climate change in the continent maritime. And finally, for the summary, for 20 years, ER and other instruments have provided the scientific community with high resolutions atmospheric and ionospheric observation data. And this has opened the opportunity to detect detailed dynamics of the equatorial atmosphere and its correlation with the global circulations. And information from the ER has produced significant new finding and improve our understanding in atmospheric dynamics in the equatorial region, including the coupling processes. And understanding of atmospheric dynamics using this ER has potential to contribute to more accurate space and terrestrial weather and climate prediction, which have important application and benefit for the society. And the ER project has promoted intensive international research collaboration among many institutions in Indonesia, in Japan, and other countries. And the ER project has also contributed to increasing knowledge and technical skill of many researchers in Indonesia and other countries, and also has inspired students and next generation of scientists. And the future development of the more advanced MU radar has the potential to further expand our understanding of the Sun-Earth interactions, and also in line with the Indonesia Space Master Plan to develop the decision support system application supported by integrated atmosphere and space observation and models. I think that's all my presentation, ladies and gentlemen. Thank you very much for all your attention. If you have any questions, you can address me to the email shown. Thank you very much.
Thank you very much, Dr. Didi Satyadi, for the thoughtful talk about past and future AR for supporting decision support system in Indonesia for entire development sectors. Ladies and gentlemen, this session already finished. The next agenda will be handled by the Master of Ceremony. Thank you very much.
Indonesia memiliki potensi maritim yang melimpah, meliputi energi, mineral, minyak bumi, dan gas alam. Potensi produksi ikan tangkap yang sangat besar, perhubungan laut, dan pariwisata bahari dengan nilai ekonomi lebih dari 15.600 triliun rupiah per tahun. Oleh karena itu, pengamatan terhadap kondisi cuaca di laut sangat penting terkait keselamatan pelayaran bagi para nelayan yang menangkap ikan dan transportasi laut lainnya. Pusat Sains dan Teknologi Atmosfer (PSTA) merupakan pusat satuan kerja dari Lembaga Penerbangan dan Antariksa Nasional atau LAPAN yang bertugas melaksanakan kegiatan penelitian, pengembangan sains dan teknologi atmosfer serta pemanfaatannya untuk mendukung pembangunan nasional. Mengembangkan sistem embaran maritim atau SEMAR merupakan sebuah sistem pendukung keputusan atau decision support.
Thank you, Dr. Erma. If you feel satisfied with the session just now, you can push the button reaction in below of your layer.
All right, the second session of this symposium will be moderated by Dr. Nur Somadi. Dr. Nur Somadi is a young researcher in Research Center for Atmospheric Science and Technology, National Agency of Research and Innovation, BRIN, And for your information, he is a chairman of this international conference increase and the 6th ARN Symposium. So ladies and gentlemen, please welcome Dr. Nusomari.
Thank you very much. Good afternoon, everyone. I think we should take a break for 10 minutes. So please wait for 10 minutes, then we will come back in 10 minutes.
Indonesia, located in the equatorial region, is one of the most important areas for the global atmospheric studies. Since the early 1990s, Kyoto University has been conducting various research activities with Indonesian researchers using radio sound observation and small radar in many areas in Indonesia. Research Institute for Sustainable Hemisphere Reach, Kyoto University, Japan, and Indonesia representative by National Institute of Aeronautics and Space of Indonesia, LAPAN, established a collaboration for equatorial atmosphere radar, ER. In March 2001, the ER installed in Kota Tabang, West Sumatra. This is the reason for the establishment of LAPAN Agam in 2001. This is the beginning of the new history of equatorial atmospheric observation. ER is a large Doppler radar with a circular antenna array of approximately 110 meters in diameter and 563 element Yagis. The system configuration of AR makes it possible to direct the antenna beam by electronic control up to 5,000 times per second. The ER transmits an intense radio wave of 47 megahertz to the sky and receives extremely weak echoes scattered back by atmospheric turbulence. The ER can observe winds and turbulence in the altitude range from 1.5 to 20 kilometers to troposphere and lower stratosphere. It can also observe echoes from ionospheric irregularities at heights more than 90 kilometers.
Selamat ulang tahun yang ke-20 untuk Ekuator Atmosfer Radar. Biar!
Technological advancement has transformed an imaginary frontier into a real place to live. When spaces have no borders, all we need is acceleration that provoke thoughts to find an answer for every challenge. Today, connectivity is fundamental to accomplish developmental missions. Therefore, transportation that connects every corner is indispensable. Through scientific experiment, investigation, and advancement by an experienced technological institute, N219 and N219 Amphibi are made. N219. These are the future mode of transportation that, equipped with high readiness level, a paramount innovation. For fast mobility, to reach every remote destination with a runway of a solid land or soil under 1,000 meters, not only for a logistic and medical transport in disastrous area, N219 also make every beautiful destination reachable. Next development, N219 Amphibi. Air transportation that can take off and landing from land or sea, equipped with landing gear to reach every beautiful corner of the country, supporting tourism, explore a new destination. N219 and N219 Amphibi, a mode of transportation for opening new frontiers to reach faraway places, undiscovered spaces. An innovation for exploring new horizon, the long-awaited answer for region-based connectivity. Technology has been a crucial component for developmental acceleration. Ensuring national security is not enough by deploying border guards. An integrated surveillance system is urgently needed, a system that can provide accurate information. From a long collaboration among research institutes in Indonesia, a future security device has been born. Elang Hitam, Medium Altitude Long Endurance UAV, an innovation and collaboration between Agency for the Assessment and Application of Technology, BPPT, and Indonesian Aircraft Industries, Dirgantara Indonesia, a medium-altitude, long-endurance UAV with the same class as MQ-9 from USA and CH-4 from China. An innovation of defense system, the vanguard of Indonesian surveillance system. An intense and high-mobility drone. Its control system is integrated with the operating system. A device that monitors a vast area from the sky to safeguard the most remote corner in Indonesia. It strengthens our defense system, assuring the security in developing the country, ensuring the safety for every soul to grow. Nature is beautiful. Not only about expansive ocean, but also the chain of islands, the span of mountains, and endless winding road. Nature is rich. But when talking about nature, it is also about the potential of natural disturbance. That comes any time, with no alarm. Natural disturbance is unpredictable. Technological advancement has taken us to a new chapter. Innovations were the foundation for every change, giving us hope, certainty, safety. A device that brings massive benefits. Extensive coverage monitoring system that send alerts and precise information to other devices that transmit signals to save our life from natural disasters. Remote sensing satellite by National Institute of Aeronautics and Space, LAPAN. Utilize and processing the satellite image data to map potential disaster, detect the fire spot, flood, and landslide. Hotspot detection results data produced by satellite image of LAPAN acquisition is utilized by the Agency for the Assessment and Application of Technology, BPPT, to apply AI-based weather modification technology to prevent forest fire. The artificial intelligence for forest and land fires is made using satellite image data and observation tools. And then the results are used in weather modification technology operations to reduce forest and land fires. LAPAN is developing A2 and A3 satellite, which generate automatic identification system, AIS data, to monitor ship movement. Besides LAPAN, BPPT is also developing AIS by utilizing transceiver-based radio frequency. AIS data is used for various needs, such as illegal fishing monitoring, ship accident prevention, and others. LAPAN is currently developing the LAPAN A4 and A5 satellite. LAPAN A4 satellite has built-in remote sensing to observe Earth's surface, mountains, and marine observations. A5 LAPAN satellite will have AIS, IoT, and other contents to connect various early warning sensors detector. Includes data communication with BPPT Tsunami Boy. Module consists of different kinds of sensors, are planned to be used as an instrument of data communication between BPPT, Indonesian Tsunami Early Warning System, INA TEWS, Boy in the Sea, with ground stations on the land as a unity of an early warning system to reduce the impact of the tsunami. INA TEWS uses a DSS decision support system device, can process information obtained from a land and sea monitoring system to determine tsunami risk levels after earthquakes. As time goes by, natural disturbance become more uncontrollable. More and more disaster will occur in the future. However, we realize that innovation should never stop, because it is the key for having a peaceful life.
Thank you very much, everyone, and thank you for still attending in this last session of Zoom meeting. And in the last session, we have 4 invited speakers. The first speaker is from Professor Hiroyuki Hashiguchi. And then will be continued by Dr. Wahyudi Hasbi. And then the third is from Professor Masatomo Fujiwara. Then the last from Professor Sulaiman Yusuf. Please welcome Professor Hiroyuki Hashiguchi, who will present about ozone. Professor. Layer and ozone vertical distribution in tropical tropopause layer. Please welcome Professor Hashiguchi. Time is yours.
Okay, thank you very much, Edison. Okay. Okay, I'd like to talk about the observations of the turbulent layer and the ozone vertical distribution in the tropical layer. And this is a result of the master thesis of the second author, Hashino-san, who has already graduated in this March. Tropical tropopause layer, TTL, is the transition region between the troposphere and the stratosphere, which is unique to the tropical region. At TTL, stratosphere-troposphere exchange is being carried out. And also, it is also affecting global climate change. Two important processes that contribute to the stratosphere-troposphere exchange have been pointed out. One is the associated with the equator Kelvin wave, which is the predominant eastward propagating wave in the TTL. And the other is the deep convection that reaches from the troposphere to the TTL altitude. And the researches using satellite observations and the analysis data have been conducted so far, but there are still uncertainties. So it is necessary to understand the phenomena through high resolution observations. So equator atmosphere radar observations are one of them. So equator atmosphere radar is the Doppler radar operating at 47 megahertz and is located at the Koto Taban, West Sumatra. It consists of the 560 three-element Yagi antennas forming circular antenna array with diameter of approximately 110 meters. And this is the active phase array system, so which allows the flexible beam steering path-to-path basis. Here, I'd like to introduce the previous researches by using the equator atmosphere radar. Fujiwara et al., Yamamoto et al., and Mega et al. Have observed intermittent turbulence layers with a thickness of about 1 kilometer at the TTL using the equator atmosphere radar, which also contribute to the vertical transport of the minor constants. There are two possible causes for the generation of the turbulence. One is the theory that the convective instability occurs due to the breaking of the equator Kelvin wave, and the energy of the waves dissipate at turbulence. The other theory is that the equator Kelvin wave is distorted from the sinusoidal waveform, making it easier for the turbulence due to the shear flow instability to occur. So we analyze the turbulent layer generation and the ozone distribution fluctuation associated with the equator Kelvin waves and the deep convection based on the observation campaign in 2019 to 2020. The data used in this study is as follows. Since this year, the International TTL Observation Project, Strateore 2, is scheduled to be conducted mainly by the French and US groups. In the pre-campaign of the Strateore 2, 8 superpressure balloons were launched from the Seychelles Island from November 2019 to February 2020. Latitude range of about approximately 10 degrees was formed from the west to east. And data were obtained for 1.5 laps. And the two types of the balloons with diameter of the 11 meters and 13 meters were used for observations at about the 18 kilometers altitude in TTL and 21 kilometers in the lower stratosphere respectively. And during the first half of the Strateore 2 pre-campaign, we conducted the intensive observations at the EL site for about 2 weeks from the November 22nd. In addition to the continuous observations of the equator radar, ozone zone days and the radio zone days were launched once or twice every day. And for long data analysis, in addition to the ozone data from the low Earth orbit, aura MLS, and also ECMWF ERA5 DNS data were used. As you know, radio zone observations use rubber balloons, and they provide the atmospheric parameters in the vertical direction with the ascending speed of about 5 meters per second. The flight time is about 2 hours, and usually 1 second sampling data are obtained. On the other hand, using the super precious plastic balloons, we can observe an almost constant altitude while horizontally moving by the wind. It can fly for several months and can obtain the sampled data every about 30 seconds. First, I will describe the case study of the case study result of the intensive observation campaign at the EL site in 2019. Upper panel show the time-hand cross-section of the zonal wind and the potential temperature anomaly observed by the radio zondes launched from the EL site. These cross signs indicate the cold point topos, which is defined by the lowest temperature. So you can see the wave structures propagating downward. And such a wave structure was not seen in the meridional wind, so it is considered to indicate characteristics of the equator Kelvin wave. And the lower panel shows the height profile of zonal winds and the potential temperature from November 13th to the December 4th. When the wave amplitude is particularly large, the phase of the potential temperature is about 19 degrees ahead of the zonal wind. So this is consistent with the feature of the equator Kelvin wave. From the November 13th to December 1st, here the condition of the wave breaking satisfies that the distortion is large near the cold point topos, and the amplitude is larger than phase velocity. So since December 2nd, the amplitude has more increased, and a very strong easterly wind has been observed. The wave structure is significantly distorted near the cold point topos, and the zonal phase velocity of the equator Kelvin wave is estimated to be 17 meters per second. And the amplitude of the zonal wind is 70 to 20 meters per second on December 1st. So it exceeds the phase velocity, so there is a possibility of the wave breaking. So these figures show the turbulent intensity observed by the ER during the same period. Left panel shows the echo intensity by the oblique beam, which is considered to be almost isotropic turbulence echoes. And the right panel shows the turbulence energy dissipation rate estimated from the spectral widths. So turbulence appears near the cold point topos from the November 29th. From the evening of December 1st to the 3rd, the turbulence intensity increased and its altitude decreased with time. And this is consistent with the distortion and the breaking regions of the equator Kelvin wave. So in other words, the turbulent layer detected here may be due to the distortion or wave breaking of the equator Kelvin wave. The vertical flow observed by the ear are plotted from the troposphere to the lower strata in this period. In the afternoon, large vertical fluctuations suggesting the convective system were observed, especially in the afternoon of December 1st. A tall fluctuation range was observed. In this case, it is considered that deep convection affected the region where the equator Kelvin wave was distorted and the shear increased. So KHI was more likely to occur. This figure shows the time hat cross-section of the ozone mixing ratio observed by the ozone zones launched from the ear side. But only the data launched in the morning time were shown. The area with strong turbulence is circled here. Top right panel shows the height profiles of the temperature and ozone mixing ratio. And the bottom panel shows their anomaly. The lowest temperature is particularly low on December 1st, with a sharp increase above the cold point tropos. This is thought to reflect the distortion of the Kelvin wave. It is thought that such temperature fluctuations narrow the altitude range of TTL and appears a rapid increase in ozone. It can be seen that the ozone has a sharp vertical distribution change in the presence of the turbulence. The division profiles of the temperature and the ozone show the similar fluctuations, and the temperature fluctuation due to equator Kelvin waves have a dominant effect on ozone fluctuations, and the turbulent mixing is considered to be secondary. The next case study is out of the long duration balloon observations and the atmosphere rate observation are shown. Eight superpressure balloons were launched in the Stratore 2 pre-campaign, but we used 3 balloon depths that flew the TTL altitude. Upper panel shows the time variation of the passing longitude of 3 balloons, and 100 degrees east correspond to the longitude of the equator atmosphere radar. They were launched from the Seychelles Islands every about 8 days. But from the January 7th, 3 balloons flew at the almost same longitude. So they maybe observed the same large-scale disturbance. Also, at the end of the January, it can be seen that the movement of the eastward is stagnant just near the ear. And the lower panel shows the bandpass filter extracted from the zonal wind and temperature observed the 3 balloons with a period of 4 to 10 days. Waves that appear to the equator Kelvin waves increase in the amplitude at the end of January and then attenuated. This suggesting that the Z block here. These figures show the time height cross-section of the echo intensity and the vertical flow observed by GER. And the turbulent layer echoes exist since the evening of the January 20th. From January 25th to 20th, the fluctuations of echoes and the vertical flow, which correspond to deep convection system is observed every afternoon. These suggest that turbulence was generated by the effect of the distortion and breaking of the equator K-beams and also deep convection.
I'm sorry, Sensei, you have 2 more minutes.
Okay. Yeah. We then statistically investigate the relationship between the turbulent altitude and the ozone using long-term data. For static analysis, we examined how to determine the turbulent layer altitude from the year day to day. So the SN ratio is used as the index of the turbulent intensity. In order to extract only the turbulent layer of interest, we set such a threshold and use the SNR in the region satisfying these the index of turbulent intensity. The altitude of the maximum value of this daily average is defined as the altitude of the turbulent layer. So we compare the turbulent parameters obtained by the ER with the ozone mixing ratio data of ERA5 reanalysis. It seems that the turbulence altitude and the ozone distribution, they are linked. When a turbulent layer does not exist, there is a tendency for the ozone below the TTL to be relatively high. And the left bottom figure shows the average profiles of the ozone mixing ratio observed all MLS in the northern winter from the 2005 to 2090, when turbulence is detected and also not detected by the ER. When turbulence is not detected, there is a tendency for more ozone at the bottom of the TTL. So this is a summary of the relationship between the turbulent layer and the vertical distribution of ozone. When the equator Kelvin wave is not prominent, ozone shows the a profile that gradually increases from the altitude of about 14 kilometers. On the other hand, when the equator Kelvin waves distorts the area near the core point topos, as if it were crushed up and down, a turbulent layer is generated, and the ozone distribution rapidly changes at that altitude. And when the distortion disappears, ozone shows a relatively gradual distribution change around 14 kilometers. So in other words, it can be interpreted that the observed ozone distribution fluctuates due to the local expansion and contraction of the TTL altitude width due to the distortion of the equator Kelvin wave, and the ozone also occurs. Conversely, monitoring of the turbulent layer with equator radar would be a proxy for TTL fluctuations due to the equator Kelvin waves. Okay, this is summary. Thank you very much.
Thank you very much. Give applause to Hashiguchi Sensei and for the nice presentation. Unfortunately, we don't have much time for discussion. And then if you have a questions, you may ask questions through a chat room to Professor Hashiguchi.
Okay, thank you.
Then we'd like to continue to the second invited speakers. Will be delivered by Dr. Wahyudi Hasbi. He will give a presentation entitled "Small Satellite Supporting Disaster Early Warning System." To Dr. Hasbi, please. Time is yours.
Thank you so much, moderator Pak Nur, for this opportunity to present our current research in satellite technology. So good day to all of you. So this is a pleasure for me to present you the small satellite research and development and its application in Indonesia. So as we all know that Indonesia is a quite big country. We have 17,000 islands. And then since that we know that we really need this space technology for the development of the country. Since then, we know that in 1976, we are the third country in the world using the first domestic satellite telecommunication system. And then LAPAN has been established in 1963. So we start to apply the space technology for our country's development until now. So, and then we can see here that there are two types of space technology actually. So first is if we want to make a technology demonstration or we want to make the operational satellite system, and then both of these will have different parameters and output. As we can see here, the technology demonstration is typically to evaluate the result of our experiments or demonstrations, or if we want to develop the products or become an expert of this technology. And then, but for the operational satellite system, of course, we will need the reliable ground station and application system. We want to deliver high-level user products, or we want to give the high service level agreements. But the other hand, we also have to think about life cycle cost of the operational satellite system. And then so we also see that there are several models of accessing satellite technology. All those, it will depend on the in-country future manufacturing or intelligent future procurements or educations and science in the country itself, and also how effective the satellite operation is. And then if we compare here, so the easiest way is of course just to buy the satellite data. And then if we want to get more data and more, we can have the leasing fraction of the capacity until if we have enough resources, we can go ahead for full ownership of the satellite system. And then we can see here the three factors is like price, of course, will be increased if we want to have the full ownerships of the satellite system. Responsibility also will be getting higher, but we have very higher independency and also a priority to use the satellite, of course. And in LAPAN, why we use a small satellite? Because at first is the small satellite will have a short satellite time development. We can have a smaller team and low cost, including the launch. As we know, the current launch cost is 30,000 to 40,000 US dollar per kilograms. So that the smaller size of the satellite will be cheaper for the launch. So another thing is we think that the small satellite will have a low risk because we can use the component of the self, and we can use the concept of fly, learn, refly philosophy, and the faster development time of course. And then we can use this platform, especially in high risk orbit, if you want to test the component, for example. And this also can be used for new missions if you don't want to risk the bigger satellite. And because of its smaller factor, then of course it's relatively low cost. And then sometimes it can be used for a non-small satellite to reduce the risk. So now we can also see that there are a lot of CubeSats because it's easy to mass productions, and of course because it's CubeSat, so the cost for the launch also will be cheaper. And then what is the strategy that we are doing in Indonesia is we go for small and micro satellite program. So at the beginning, we start with development of capability, and then later on, we will go ahead for development of the missions and technology. For the development of capability, we are focused on the knowledge, skill, and experience on integration, test, launch, and operations. And then at the beginning, we start with design to cost satellite. As we know, we don't have enough budget, of course, to create a big satellite. So we have to think or use the philosophy of design to cost. And then at the beginning, we start with the development of LAPAN-A1, and then later on, we extend the performance with LAPAN-A2 satellite and LAPAN-A3. And currently, we are in between focus on space application, and we want to make the known and proven missions and dedicated new missions like in LAPAN-A4 satellite later on. So this is our roadmap. We can see here that we launched already in 2007. We have LAPAN-TUBSAT satellite for video surveillance, and LAPAN-A2 for AIS and IPRS, the voice repeater and digital camera for high resolutions. And then in 2016, we have LAPAN-A3 satellite. We'll have it has multispectral imagers, and then currently we are waiting for launch of LAPAN-A4. This LAPAN-A4 satellite has AIS, science magnetometers, multispectral, and so on. And also we are currently designing the satellite communication constellations. And furthermore, we will also apply for synthetic aperture radar and go on for SAR operational later on, like in 2035, 2040. So this is the satellite orbit. You can see here our LAPAN-A2 and LAPAN-A3. LAPAN-A3 is the orbital polar satellite. So you can see that it starts from north to south, and LAPAN-A2 is in the equatorial between west to east, and LAPAN-TUBSAT as well is in orbit of same orbit as LAPAN-A3 in the polar orbit satellite. So you can see here the footprint of our camera. So this is LAPAN-A3 with a very SWAT width of the camera multispectral as well. And then you can see here the digital camera of our LAPAN-A2 satellite. So this is our first satellite called as LAPAN-A1 or LAPAN-TUBSAT. So at the beginning, we learned how to make the satellite, how to design and integrate, test all the components, making the payload, including how to control the attitude of the satellite. Like here, you can see that even though the satellite is flying or orbiting with the speed of 7 kilometers per second, but we can see here that we are like hovering on the top of mountain and see around, just like you are as an astronaut or you are in helicopters. So this is another example. How can we hovering over the Merapi Mountains with the speed of the satellite about 7 kilometers per hour per second, and you can see here we can monitor the Merapi Mountain. And then we stitch the video image of this. We make an image, and then we can enhance and make the georeference process of it. And then you can see here the image layout, and then further we can make land use information out of the image, of course. And then this is our LAPAN-A2 satellite. So far, on 28 September next 2 weeks, I believe, we will reach 6 years in orbit. So far, we operate the satellite for more than 4,600 hours for TTNC. We collect more than 354 million AIS data for ship monitoring. We collect the 959 hours for operational voice repeater for amateur radio, especially during a disaster. We also get the high resolution image, about 756 kilometers square. And then we have more than 1,253 hours operational package reporting system, just like SMS message. And then this is our LAPAN-A3. It has been launched in 2016. Now it's 5th years already. So we operate the satellite for more than 1,700 hours. We collect 202 million AIS data, and we also collect the magnetometers or Earth magnetic field, more than 7,000 hours. And we collect 7 million kilometers of high resolution image and 324 million kilometers square of multispectral images like this one. So this is some example how we help our colleague in Vietnam. For example, they got some forest fire in Vietnam, and they request us to give them the the condition or the image of their area, and then we take the image of the Vietnam or of the forest fire, and by this data they can make out of this image, they can make the information how big is the forest fire there. And we also get the request from our colleague from Hokkaido University. There is a heavy flooding in Kagoshima in Japan, and then we also took the image for them as well. So this happened in 2019 as well in Kagoshima. So this is some image requested by students in the high school of students in Japan. So they request us to take some image of their area, and then this is the image that we took on 24 July on 2021. So this is might be also interesting for you that our LAPAN 83 satellite also have a Earth magnetic field sensor, so that we can measure all the Earth magnetic point here, and then we can compare with the SWAM satellite. So you can see, you can compare the result. We also make a study now currently under review in Q1 journal. So we compared the result with AGRF 12 model, and we found that 94.3 of scalar component, we have residual less than 300 nanotesla and so on here. And based on the discussion as well, so the Earth magnetic field can be used as well for earthquake signature precursor, as mentioned in Nature journal as well. So this is another example. How can we image the Krakatau mountain during a disaster or during the eruption? You can see here before the eruption happens. So the color is all with red, means a lot of vegetation, but you see here after the eruption, there is one island is we cannot see the vegetation, maybe because of the ash covering the island itself. So this is another example. How can we monitor the disaster in Indonesia? This is a case in Petobo during the liquefactions in 2018 for Palu earthquake. We monitor the Mount Agung eruption in 2019, and also in Mount Rinjani during the Lombok earthquake in 2018 as well. And then this is another usage of our satellite. We use the satellite as well for communication support during a disaster. You can see here, so that you can use only handy-talkie with the 5 watts RF power is enough, or with their own antenna, or you can make your very small antenna and very cheap, so that you can use this repeater satellite in case you got some disaster. So you can see here some video of this guy. So this gentleman only using handy-talkie, and he talks with her colleagues more than 2,000 kilometers away. So only by using this handy-talkie. So the record that we have found that we got one communication between Sabang Island here in Aceh directly to Maluku through our satellite. So it's more than 3,000 kilometers. The satellite also used not in Indonesia but also used in Brazil or in Latin America as well. So they use the satellite as well during the weekend. We switch on the satellite in their area. So this is our social media during regular missions. We inform the public how the satellite works, but during a disaster, all the schedule is only dedicated for emergency communications. So besides that, we teach, of course, all of our people, typically in the potential area of disaster. You can see here, we teach the public how can they use the satellite by making a very simple antenna. For example, if they want to use their own antenna, or they can just directly use their handy-talkie antenna directly. So this is the area that we teach the people. And then you can see here how can the satellite also be used like SMS message. So you can see here the digital message from the amateur radio they send between them. So they say hello, they send a message by using our LAPAN 82 satellite as well. And then for maritime, the satellite has been used for maritime monitoring. A lot of situation happens in our maritime domain. So you can see here in 2016, we found the last AIS message sent by the crew of a ship called Brahma 12. And by the time the crew is kidnapped by terrorists, and then they kidnap during that time. And this is some example how we monitor the sinking ships. So this ship is bringing nickel, but there is a report that they cannot be communicated anymore, and we found that the last AIS message is stopped there, and then we try to find them, but unfortunately we cannot see them in the ocean anymore. And then this is some example how can we identify ships with our satellite. So there is a rumors or in the news saying that there is a mysterious ships. But after we track these ships, actually this is not a mysterious ship, but this is ships that carry out their employee to other area or they want to send it back to their country. So with all the things, so we start with the research and development of design and the component of the satellite, AIT, assembly, integration, and test of the components, launch preparations, and launch an early orbit phase, mission operation. The whole change can be done already here in Indonesia for the satellite development. So you can see here how can we develop the satellite. We bring it to the launcher, and of course to operate the satellite itself. So this is our further satellite, LAPAN F4. LAPAN F4 is our next satellite. We plan to launch it in next year. This is a quite big satellite. It has a 150 kilogram mass, and we will bring a next generation AI system so that it can detect more ships. And we also bring Hokkaido University bolometers. So the bolometer will be hosted by our satellite. And of course, we will bring also the Earth magnetic field again to measure all the Earth magnetic in our Earth. And then we will bring a new medium resolution multispectral and high resolution multispectral camera as well. So another
Dr. Hasbi, yeah. I'm sorry.
Yes, it will become fast. Yeah. So this is the Leo constellation, our next satellite, the mission for supporting disaster early warning system for maritime surveillance and machine-to-machine and IoT systems. So this is already in the design phase. So we'll see it very soon. So this is the whole change of the facility that we have. So we have thermal vacuum to test all the components, vibration test, the EMC for testing all the RF components and so on. So we have also ground station in Indonesia and also in North Pole. So we place our ground station there as well. So with that, I conclude my presentation. Thank you very much for your kind attention. I give it back to MC. Thank you so much.
Thank you very much, Dr. Hasbi. Please give applause to Dr. Hasbi. And we still have 1 minute for discussion. Is there anyone want to ask question to Dr. Hasbi? Please raise your hand, or you can ask directly through your Zoom account. Okay, I have a question to Dr. Hasbi. You mentioned about a small satellite can be used to early warning system. Could you please explain in more detail what kind of disasters? Or you talk about this satellite can be used to communicate each other using radio, amateur radio. Okay, please, could you explain more detail?
Okay, thank you for the interesting question. So actually, what we mean by disaster mitigation support is, as we remember in Palu earthquake, what happened is there are a lot of sensors already been there, but because of the earthquake happens first, so all the terrestrial is shutting down, so nobody can see what happens in the sensor anymore. So that's the reason why we need other means of satellite. So we other means of communication, which is satellite, right? So and then actually there are a lot of satellite already been used for communicating with all the sensors like earthquake sensor, magnetometers, or on the ground and so on. But the problem is too expensive. That's the reason why we bring these ideas to develop our own satellite so that the cost will be lower, and then we can use especially for early warning disaster. So That's the answer. And then this is also has been proved in the Palu earthquake again. You remember that during the earthquake, there is no power, no electricity, nothing is there, and the person, the amateur radio only use handy-talkie, and then they can inform what really happens in that area. So this technology has been proven already by our satellite. Thank you.
Okay, great. Thank you very much for your very clear explanation. Then we continue to the third invited speakers, Professor Masatomo Fujiwara. Professor Fujiwara will talk about how overview of the Spark reanalysis intercomparison project. Please, time is yours.
Thank you. Thank you very much for your introduction. Let me try to share again. Thank you very much for your introduction, and thank you very much for giving me an opportunity to talk about this project. My name is Masatomo Fujiwara from Hokkaido University. Today I will present overview of the Spark Reanalysis Intercomparison Project, SRIP, during 2013 to 2021. SPARC stands for Stratosphere, Troposphere, Processes, and Rolling Climate, and this is one of the WCRP core projects. My co-authors are Gloria Money, Leslie Gray, Jonathan Wright, and the SRIP team members, which compose of about 100 colleagues from the SPARC project and also from reanalysis centers. First of all, congratulations to the 20th anniversary of the EAR. Many years ago, I visited several times there and launched ozone sound and water vapor sounders. So this is a good memory for me. So now, coming back to the reanalysis. So first, what is a global atmospheric reanalysis? A global atmospheric reanalysis consists of a global forecast model and an assimilation scheme assimilating various observations and various observational input. And the system fixed over time and integrated for many decades, and produces best estimate of past atmospheric states for studies on weather and climate processes, and also for validation of various climate models. And current reanalysis producing centers, including ECMWF, European Center, JMA, Japan Meteorological Agency, NASA, NOAA, and some others. So we have several reanalysis products, and our question is which is better or which is closer to the truth. So the introduction to the SRIP. This project was proposed in 2011 and started officially in 2013. The goals of SRIP are to create a communication platform between Spark-related researchers and the reanalysis centers to better understand the differences among current reanalysis products and their underlying causes, and to provide guidance to reanalysis data users by documenting the results of this reanalysis intercomparison in peer-reviewed papers and the Spark SRIP report, which was just published from the Spark website as an early online version. And with these activities, we are to contribute to future reanalysis improvements. And this is a list of global atmospheric reanalysis currently available and evaluated in this Spark SRIP report. We also have reanalysis center contact persons for this project from ECMWF, JMA, NASA, and NOAA. And we primarily evaluated full input global atmospheric reanalysis, such as ERA Interim, 055, MERA2, and CFSR. But we also looked at surface input reanalysis like 20CR, CER, 20C. Regarding the ERA 5, which is the most recent reanalysis product from the ECMWF, because this became available only 2018, so we only have partial evaluation of this project. The SWIP has 12 chapters. The SWIP report has 12 chapters. Chapter 1 is for introduction, and chapter 2 is for description of the reanalysis systems. And this chapter 2 should be very useful for any reanalysis data users, not only Spark people, but also any data users, because we have a good summary of the technical details of each of the 12 global atmospheric reanalysis systems in a rather concise manner. And then chapter 3 is for overview of temperature and winds. Chapter 4 is for overview of ozone and water vapor in the upper troposphere and stratosphere. And then chapter 5 is for blue adoption circulation. Chapter 6 is for extratropical stratosphere-troposphere dynamical coupling processes. And chapter 7 is for extratropical upper troposphere and lower stratosphere region. Chapter 8 is for tropical tropopause layer, TTL. And chapter 9 is for quasi-biennial oscillation, QBO. Chapter 10 is for polar processes. And chapter 11 is for upper stratosphere and lower mesosphere region in the reanalysis product. And finally, chapter 12 is for synthesis summary. And we also have the special issue on the SWIP in the journals Atmospheric Chemistry and Physics and Earth System Science Data. And currently we have 48 papers there. And we just published an early online release version of the SWIP report in the Spark report series, which have a total of about 600 pages. And you can download it from this website or from this QR code. So now I will pick up some SWIP evaluations, actually 3 topics from chapter 3, chapter 8, TTL, chapter 9, QBO. And also I mentioned one paper, one very recent paper by Uma et al. Using ERA, EAR, and evaluated reanalysis vertical winds. So the first one is time series of global and zonal mean temperature time series, and looking at inhomogeneities of the reanalysis products. This is taken from MERA2 reanalysis, time, altitude, distribution of global mean temperature anomalies. And these anomalies are calculated from the monthly climatology of each reanalysis, in this case, MERA2. This plot is to look at the degree of homogeneity of the reanalysis temperature time series. So if we look at the tropospheric region, we can see global warming over time from 1980 to 2014, and global cooling in the stratosphere, both due to increase of the greenhouse gases. We also see lower stratospheric warming, strong warming signals due to very large volcanic eruptions, El Chichon in Mexico and Mount Pinatubo in the Philippines. And we also see some strong El Nino events like 1998 event and 2010 event. But in particular in the upper stratosphere, we also see some artificial jumps due to introduction of new satellite instruments. For example, here is the new ATOPS ARMS-A instrument introduction here. And for the MERA2 case, 2004 is the introduction of the MLS temperature observations in the system. So in this case, we see a strong jump. And this is not the climate signal, but the artificial jump due to the artificial reasons. And now this figure shows the same MERA2 here, and then we show several other reanalyses, including ERA5, the most recent reanalysis from European Center. So the key findings from this figure include more recent reanalysis from all centers are better than their previous versions. For example, JERA55 is better than JERA25. You can see JERA25 shows several jumps here, but the JERA55 becomes smoother. However, due to changes in available data sources, drift and jumps in the long-term temperature time series can occur. And these irregularities are greatest above 10 hectopascal in the upper stratosphere in any reanalysis system. Therefore, greatest caution is advised when determining trends with using reanalysis temperature datasets, particularly above 10 hectopascal, but also below 10 hectopascal level in the lower stratosphere and perhaps even in the troposphere. And temperature biases exist among the various reanalyses, even in the upper troposphere, lower stratosphere region, especially before 1998. Temperature do not harmonize until GNSS radio occultation temperature observations are used to lock in the temperatures in most of the reanalyses after 2005. And next topic is from chapter 9, the tropical tropopause layer. And this chapter discusses various aspects of the TTL, like temperature and tropopause characteristics, clouds and convection, diabatic heating rates, transport, wave activity, width of the TTL, and finally, South Asian summer monsoon system. And here I pick up two topics. The first one is the anomaly time series of the cold point tropopause temperature, pressure, and height time series. And anomalies are calculated with respect to 22 to 2010 periods. And key findings from these figures include that the NCEP anchor reanalysis 1, the orange curve, is a clear outlier, being much warmer than others, particularly before 2005. And however, differences among the more recent reanalysis are also relatively large. You can see the differences around here. With ERA interim, blue curve is coldest, and the CFSR, green curve, is warmer. And the differences are as large as 2 Kelvin in the 1980s. Regarding the internal variability in cold point pressure and altitudes, these show better agreement among the datasets compared to the temperature dataset at the cold point. And the agreement improves over time, with the most consistent result found for the period after 2002, when the GNSS radio occultation temperature observations are simulated in most of these reanalyses. And another topic from the TTL chapter is the climatological temperature anomaly at 100 hectopascal level during the June, July, August season and December, January, February season from MERA reanalysis, CFSR, ERA interim, and JERA55. And we can see that the 100 hectopascal temperature patterns, like colder temperatures here and the warmer temperature in the Western Indian Ocean in JJA, and generally very cold temperatures over the Western Tropical Pacific in DJF. These patterns qualitatively among different reanalyses. However, in terms of you can see quantitative differences in terms of the degree of coldness here or the warmth of these regions here. So you have to be very careful about which reanalysis you're investigating, and for particular diagnostics for which the quantitative differences are very important. And moving to the chapter 9, the quasi-biennial oscillation, QBO chapter. The QBO is the oscillation of zonal winds in the tropics, westerly, easterly, westerly, easterly, with the period about 27 months on average, and still slightly longer than 2 years. And this oscillation is due to wave mean flow interaction, and therefore momentum flux of non-orographic Wavy waves and resolved equatorial waves are very important. And QBO is the tropical phenomena, but also there are several global impacts on circulation and composition, like ozone layer. And chapter 9 discusses monthly mean equatorial variability, tropical waves and QBO forcing terms, and QBO tail connections. And chapter 9 has quite many pages and quite many figures. And if we look at the overall QBO features, this is the Singapore radio sound time series, and these are reanalysis data at the Singapore location from various different reanalyses. And you can see that the reanalysis represent the monthly mean zonal wind over Singapore reasonably well. However, if we look at data closely at different levels, 10 hectopascal, 20 hectopascal, 70 hectopascal, with different colors for different reanalysis, we can see some problems in some reanalysis products. For example, at 10 hectopascal in the 1980s, MERA2 differs much, the pink colors here. And this is due to the overestimation of the semi-annual oscillation in the upper stratosphere in this reanalysis system. And if we go down to 20 hectopascal to 70 hectopascal in the lower stratosphere, you can see some outliers here in orange curves, which is NCEP reanalysis 1 and NCEP DOE reanalysis 2. They underestimate QBO in the 1980s. And the bottom figure shows the root mean square differences with respect to radio sound data. And you can see that the RMS differences are generally decreased with time for all reanalysis products. And finally, let me just mention one example of using EAR data to evaluate reanalysis vertical winds. Indian colleagues very recently published this paper in the ACP. They used radar measurement at Gadanki, India, and EAR at Koto Taban, and evaluated reanalysis vertical winds from various reanalyses. So now EAR data are started to be used for evaluation of reanalysis data products. So concluding remarks. Chapter 12 is for synthesis summary and 12.2 is for overall findings and realize user recommendations across different chapters. And some of the key points from chapter 12.2 is as follows. First one point, more recent reanalysis typically outperform earlier products. So you had better use more recent reanalysis products. And NCEP ENCOR reanalysis 1 and NCEP DOE reanalysis 2 are unsuitable for most diagnostics and should generally not be used. And studies rely on reanalysis products should use multiple reanalysis whenever possible. And all reanalysis show discontinuities. Therefore, trends and climate shift identified in reanalysis products should be carefully validated and justified by looking at several other reanalysis or even other independent observations. And finally, homogenized and continuing data records, including those from EAR, are essential for reanalysis production and evaluation. And future of the SWIP project. The final version of the SWIP report will be published in January 2022, early next year. And then after that, phase 2 of the SWIP will be started, investigating fully ERA 5, JERA 3Q, which is the newer next version of JERA 55, and several other upcoming reanalyses in comparison with previous versions. Thank you very much for your attention.
Okay, thank you very much, Fujiwara Sensei. Very interesting talk, and yeah, we have 1 minute for discussion. Perhaps there are a question from.
Can I ask a question? My name is Yamamoto.
Yes.
Yes, very interesting talk. Thank you very much. I am very impressed by the positive impact by the GNSS occultation data. After introducing the data, the error is becoming smaller. Is there any possibility of improving the model? Then the comparison of the much further data before, like 1980 or 1990 period, becoming less and less because later in the future.
Yes, we are. Yes.
The reanalysis of the past by improving the model.
Yes, that's really a good point, and we are also pushing reanalysis producing centers to do a better job for the past part of the reanalysis product. Actually, the problem is the past observations, including satellite observation in the 1980s and 1990s. There are several discontinuity in the data records and the several drifts and some biases in the observing systems. And the reanalysis centers are working very hard to homogenize or reprocess past observations that are assimilated into the reanalysis system. So yeah, that's one point. And then for the upper stratospheric region, because observations are sparse in the upper stratosphere and even lower mesosphere. So in that area, model improvements are really important to improve the reanalysis data product.
Thank you. One more very quick question. You made a very big report. How many pages is it?
Yeah, that's 600 pages. It's really large, but you can go to each chapter, which is about 60 pages, 100 pages, so it's more manageable.
Thank you very much for your effort.
Thank you very much, Sensei. Very interesting talk, and yeah, actually, I have it is surprising that NCEP reanalysis should be caution and yeah, showed outliers in tropical tropopause. And yeah, let's continue to the last speakers. Will be delivered by Professor Sulaiman Yusuf. The title is How Climate Change Drives Global Termite Distribution and Invasiveness. Please, time is yours.
Thank you very much, Mr. Chairman. Can I share my slide first? Just one, please. Before I start, I would like to confirm. Can you see my slide? Can you see my slide and hear my voice?
Yes, we can see.
Oh, thank you very much. So before that, I would like to say congratulations for the year-end 20 anniversary. So good afternoon, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh. First of all, I would like to introduce myself. My name is Sulaiman Yusuf from the Research Center for Biomaterials, National Institute of Life Science, BRIN, National Research and Innovation Agency, Republic of Indonesia. It is a great pleasure and great honor for me to invite it here and presenting as an invited speaker in the International Conference of Radio Science, Equatorial Atmospheric Science and Environment, and the 6th ARN Symposium on Humanosphere. Today, I would like to present an important topic regarding how climate change drives global termite distribution and invasiveness. The topic is a hot issue among termite scientists nowadays, as we are encountering the rapid introduction of invasive termite species into new areas that were previously unsuitable for termite to thrive and survive. Before we start talking about the issue, I need to introduce to you all when. Just a bit. When and where do termites occur? I think it is important to grab some short history about termites and their preferred habitat. Termites have existed on this earth since 350 million years ago, and they have close relationship with the cockroach. The evidence of the ancient life of termites on the earth can be traced by the discovery of termite fossil. Many termites Bertrani fossils have been found in Barcelona, Spain, and was estimated to exist 130 million years ago. And another termite fossil, an elite of flying termite, was found in Liaoning province of China and estimated to exist about 125 million years ago. So the termite mainly found in the warm climates. Most species are found in the tropical and subtropical areas such as Southeast Asia, and then North Africa and South America. They also met in the moderate climate. For example, South France, Portugal, northern part of Japan. In the tropical and subtropical areas, termites account for 10% of animal biomass and 95% of soil insect biomass. About 3,000 species of termite have been described, and around 183 83 species are known to damage a building, and 83 species of them cause significant damage. And what drive global termite distribution? The spread of termite species is driven by three factors: urbanization, global trade, and climate change. Each of these three factors is independently capable of affecting significant change in biological communities. And all three have been the subject of extensive research in the context of conservation and the control of pests. Several termite species are significant economic pests, mainly in urban area, where they attack human-made structure and become one of the most serious global environmental threat. Now, globalization has promoted the accidental transfer of animal and plant species, including termite, throughout the world. Introduction rate of alien species have been shown in match up remarkably well with global trade, modern and human-mediated event. Urbanization drive climate change and shape of the ecology and evolution of invasive termite species. The data shown in this picture, in the left picture, indicating the significant increase rate of the urban population by continent from 1950 to 2020. The world urban population today is around 4.4 billion more than the world total population in 1975. In 2020, 56.2% of the world population was urban. The rural to urban immigration often result in overcrowding, pollution, and poor sanitation, which is damaging to the environment. An increase in the use of fossil fuel will add to global warming and contribute to climate change. As shown in the middle picture, urbanization process lead to change the surface climate within cities and form what is called the urban climate. The picture showed the urban environment have a significantly higher temperature than that of rural and green area. With rampant deforestation, the number of trees is reduced. With fewer trees, we have decreased oxygen supply, decreased rain, and increased carbon dioxide in the air. This factor will lead to higher humidity. As one lead to the others, this can increase global warming and climate change. In the right picture, shows that we present how urbanization not only increased pollution and the temperature, but also lead to habitat fragmentation. Urbanization is quickly changing natural and agricultural landscape, affecting the ecology and evolution of termite and the other herbivorous arthropod dwelling in or near city. So global spread of high invasive termite species in among of most serious urban environmental threats. This slide shows the following slide is global temperature change. Since 1818, Earth average surface temperature has risen by 0.07 degrees Celsius every decade, and over time it adds up. The rate of temperature change have grown significantly more than doubling to 0.18 degrees Celsius since 1981. As a result of the global warming process, environmental crises have become the most prominent risk of our time. In the global temperature graph shown in the slide, monthly average temperature have changed over nearly 170 years. Temperature value have been benchmarked against the pre-industrial average from the 1850 to 1900. The data visualization can be touched of in two halves, each reflecting significant trigger point in global warming trend, I mean. From the 1831 to 1935 overlap with the second industrial revolution. So low-high range in global temperature increase from minus 0.4 to plus 0.6 degrees Celsius. And on 1936 to 2020 overlap with the third industrial revolution. The low-high range of a global temperature increase from the 0.6 degrees Celsius to plus 1.5 degrees Celsius and up. The global temperature graph make it clear that for several years now, average surface temperature have consistently surpasses 1.5 degrees Celsius above their pre-industrial value. In the left-hand picture, we can see that each decade hotter than the last. This slide the number of global invasive termite. And the continental region in the red letter and the island in oceanic region is a blue letter. So Evan et al. Reported that the number of recognized invasive termite species has increased from 17 in 1969 to 28 today. Invasive species are those termites that are introduced beyond their native area. And in this picture, we can see that the number of invasive termite species in temperate region is marked by the yellow square boxes. It increases significantly. The rising temperature may drive the rapid introduction of invasive termite species in the last half century. So what is the impact of the climate change? What is the impact of the climate change effect on distribution? The impact of climate change on termite population is becoming a hot topic with a significant change in temperature, particularly minimum temperature and humidity. The potential spread of termite to new areas previously unsuitable for termite survival is really possibility. It's just okay. I'm sorry. The climate change effect on termite distribution is distribution of projection of Coptotemus formosanus in Korean Peninsula in responses to the climate change. The Formosan subterranean termite, Coptotemus formosanus shiraki, have never been reported in South Korea despite its close proximity to two countries, China and Japan, where this is economically important pest has been reported. This may be due to the average winter temperature in South Korea, which is below 4 degrees Celsius in lower limit of the current distribution range of Formosanus subterranean termite. With the estimated rate of the temperature rise, winter temperature in the southern region, it will exceed the 4 degrees Celsius starting from the 2020. The Formosanus subterranean termite is predicted to become established in South Korea, probably starting from the southern trade port such as Busan. The climate change effect on termite distribution. First, record the subterranean termite Reticulitermis grassi in Switzerland. Gassini et al.
Professor Sulaiman, I'm sorry, your time is 1 more minute left.
Okay. So I will do this. So Gassini et al. Reported that the first record of subterranean termite grassi in Switzerland in investigation first detected near Lake Zurich in 2018, and the DNA analysis indicate that the termites were similar to population from the southern Spain, an area with a warmer climate. So the climate change. So the prediction of the termite invasion hotspot in 2050 under the representative concentration pathway RC 4.5. The RCP is greenhouse gas concentration not emission trajectory adopted by the IPCC. So RCP 4.5 is a scenario for long-term global emission and greenhouse gases, short-lived species, and land cover with a stabilized radiative sourcing at 4.5 watts per square meter. So the summary, the substantial economic and ecological damage caused by invasive termite is likely to increase in the future as climate change, urbanization, and globalization become more pronounced, and their cumulative interaction become more common. I think thank you very much, and thank you for attention. Thank you.
Thank you very much, Professor Sulaiman. Please give reaction to Professor Sulaiman, and maybe I will give a chance to participants who want to ask one question. Is there any question from participants? No? Okay. There is interesting talk about invasiveness of termites, especially for the climate change, climate trends. So you mentioned about increasing of species from 17 to 28 species.
Yes.
So how many, I mean, the trends for decades or?
I'm sorry, what the meaning?
Yeah, in 1960s, there was only 17 species. Then due to climate change or temperature increasing, the number of species become 28.
Yeah.
Yeah.
So yes.
So how many change? I mean, increasing of species per decade.
Oh, the number of species is increasing, but I don't know the what the species name. But actually in increasing temperature from the tropical area, what's the meaning? Invices to the what's colder area. So invasive.
Okay, I see. Thank you very much. Please give reaction to Professor Sulaiman.
Thank you very much.
And yeah, now we will return to Master of Ceremony. Please, Faldi and Cecilia.
Thank you, Dr. Nursamadi.
With the end of the symposium today, the first day of Increase event has officially ended as well.
And we will continue tomorrow with the parallel session started at 1:30 a.m. GMT or 8:30 a.m. GMT +7 local Western Indonesia time. Therefore, see you tomorrow.